Okay,
Yes, we can see you too.
okay, great. Thank you so much. I feel I have went back to 14 years ago, back in time. Bujin and I, we were in the same lab, working under Professor Biswas's supervision. And it was a great time, and it opened a lot of doors to me throughout my career. So the topic that I'm going to talk about, it doesn't look relevant to the aerosols, but actually conducting research on aerosols got me to this job. And I'm going to walk you through my journey and also explain to you what I'm doing today at Air Products. So the topic is application of LCA in framing environmental policies. But before diving into that, let's take a look at my journey. So I did my grad studies at the Sharif University in Tehran, Iran, in chemical and environmental engineering. I graduated in 2008, and then I went to Washington University in St. Louis, Missouri, to do postdoc. My second postdoc was with Professor Biswas at the AAQRL lab. And I worked on aerosols from coal oxy combustion and gasification. And I had that posted on my LinkedIn. So a recruiter contacted me and asked me if I'm interested in joining Praxair. And they were looking into the same reactions, the same processes like oxycombustion, gasification, reforming. So working at Professor Biswa's lab made me a good match for that position. So I joined them. I worked for their research facility for 3 years. And then after that, I joined ExxonMobil their research facility in New Jersey. I worked there for almost more than 9 years. And I picked up a new skill set, and that was conducting research on life cycle assessment. In the next slide, I'm going to tell you what is life cycle assessment. I guess many of you may already know, but if you're not familiar with this topic, it's something interesting to take a look at. I also manage their renewable energy programs. And then more than a year ago, I joined Air Products. And there I'm working on advocacy on climate policies. And what does that mean? There are a lot of policies in the US and in different parts of the world that their goal is to decarbonize and reduce emissions. And to be able to understand those policies is important because, like I would say, like since a decade ago, all these policies are written based on like sound, technical background and science. So they need people like you and me to read those policies that understand them and then explain them to the other parts of the company, for example, the business and the business section in the companies and explain to them what are the impacts, what are the implications to shape and frame a policy advocacy strategy in the company. And then again, the companies need people like you and me to go and talk to the policymakers when it comes to advocacy. Because again, since almost a decade ago, things have been changing. And since technology is playing an important role in shaping these policies, now science talks. And we have a seat at the table. And that's very important. I would like all the students here to remember that. So what I do at Air Products is I shape the company's strategy and advocacy. I go to the White House, to the Department of Energy, to the Treasury, and explain the company's request around these climate policies and engage them in active discussions. So, with that being said, let's go to the next slide, which is explaining what is life cycle assessment or LCA. Oh, before jumping to that, I wanted to again emphasize I got my role at Air Products because I had experience in life cycle assessment, and I also had experience in oxy-combustion, gasification, reforming. So the skill sets that I picked up at AAQRL, again, it opened another door for me to join Air Products. So you can see in my journey, being a postdoctoral research at AAQRL actually opened so many different doors to me. And I'm sure that in the future it will continue doing the same. So going back to the slide on the life cycle assessment, life cycle assessment is a methodology that you use to quantify the environmental impacts of a particular product or service. And there are different types of LCA. One is called attributional LCA. When you do attributional LCA, you look at only the direct emissions from your product. The other one is consequential LCA. When you do consequential LCA, you look at not only direct, but also indirect emissions, or they call it consequential emissions or induced emissions. There are different ways of calling them. But basically, you look at the whole picture per se. And when you do life cycle assessment, you have to define what is your system boundary. So system boundary is basically like a box that you put around the process steps that you would like to include in your calculations. And I'm going to show you in the next slide that what does that exactly mean. So let's go to the next slide. Well, actually, you have to wait for another slide to see the system boundary. Before going to that slide, I would like to tell you about renewable fuel standard and then show you the system boundary that EPA has chosen for renewable fuel standard, or RFS. So RFS requires biofuel to be blended into transportation fuel. So in your car, if your car runs on gasoline, you think it runs on 100% gasoline, but that's not the case. In the gas stations, we have 10% of the blend coming from corn ethanol. And this corn ethanol is actually mandated under RFS. So they say 10% of the blend should be corn ethanol to help with reducing greenhouse gas emissions. And what EPA has done for RFS is that they categorize biofuel based on their feedstock and their life cycle greenhouse gas emissions. As you can see here in the middle of the slide, renewable fuels, advanced biofuels, and cellulosic biofuels are those categories that I mentioned. If you look at the right-hand side, you can see that the renewable fuels are the ones that their greenhouse gas emissions are 20% lower than baseline gasoline. And the advanced fuels, including biodiesel, their greenhouse gas emissions is 50% lower than baseline gasoline. And the right-hand side, the cellulosic biofuels, they have the lowest greenhouse gas emissions, which is at least 60% lower than the baseline gasoline. And here at the bottom right-hand side, you can see the depiction of the baseline fossil fuel. They assume its greenhouse gas emissions is around 93 grams CO2 equivalent per megajoule of fuel. And then you can see, based on those percentages that I mentioned to you, what is their life cycle greenhouse gas emissions. So EPA decided to conduct consequential LCA for fuels and biofuels to decide that if you make biofuel, what category it fits in. And as I mentioned, in the consequential LCA, you look into both direct and indirect emissions. So this is actually the system boundary. So everything, all these graphic cartoons and the box that you see here, all of them together are within the system boundary that EPA has decided to choose. Meaning that if you look at the very left-hand side, and this is an example for making ethanol from corn residue, and they call it corn stover. So when you grow corn, you have leaves, stalks, um, kernels. So putting the kernels away, like the yellow grains, the edible part, you can make corn ethanol out of that. But everything else, you can make ethanol out of those too, and that would be cellulosic biofuel. So what would happen is that if you start from the looking at the left-hand side of the slide, first of all, you go and collect, harvest all these stover leftovers on the farm. Um, and then you put them on the truck, you send them to the biorefinery, they make ethanol out of that, then they put it on the truck and bring it to the end user. And any greenhouse gas emissions from any of these steps that I showed you is a direct emission. Now, besides that, we have indirect emissions, which comes from land use change and livestock change. So, for example, in the US, when the farmers see that by growing corn, you can make money more than before, because you can get actually more money from the buyers, since before corn was just like a food source, but now it's also a fuel source, and these biorefineries can pay you good money. So you have more incentive to grow corn. And historically, you have been growing corn for 1 year and then growing soy for the other year, and then do the rotation going forward. But now it's more profitable to grow corn. So what would happen is that you will grow corn for 2 years and then 1 year soy and then 2 years corn. Basically, the soy production goes down because more money is in corn. And that would incentivize other countries to cut down forests and clear out the land to grow soy. And this concept is called land use change, and then cutting down the trees, burning them, such as what has been happening in Amazon in like a decade ago. Those emissions are called greenhouse gas emissions from land use change. And that's the indirect emission that RFS has been capturing in the life cycle assessment that needs to be done. So that's what is happening in RFS, biofuels, and you can see that how LCA is the basis of RFS. Another climate policy that we have that currently I'm working on is Inflation Reduction Act. You may have heard about that a lot on the radio, in the newspaper. It has like it is giving you a good tax credit if you make clean hydrogen. And let's see what is clean hydrogen and how much tax credit can you get. So basically, clean hydrogen is a hydrogen that is life cycle. Greenhouse gas emissions are less than 4 kilograms of CO2 per kilogram of hydrogen. And I'm trying to, for some reason, my screen gets blocked by the Zoom window, and it doesn't go away. I don't know why. It's trying to deal with that here. Sorry. Okay, so here in the figure, you can see that on the x-axis, the life cycle greenhouse gas emissions of hydrogen is shown, and on the y-axis, we are showing the tax credit you can get, which is dollar per kilogram of hydrogen. And as you can see, they have different categories for the greenhouse gas emission, life cycle greenhouse gas emission, meaning that if you are if your life cycle GHG emissions is less than like 0.45, then you can collect $3 per kilogram of hydrogen. But if you are in the very last category, you can collect much less. And if your GHG emissions are more than 4, basically you cannot collect anything. So in this IRA, if you look at the figure, you can see what system boundary they have selected. They want to look into the direct emissions, but they also know that indirect emissions are very important, and they have a very good and robust climate guardrails to curb those indirect emissions. And that's what I have been advocating on for the past year, and I'm going to show you those environmental guardrails in the next slide. But first, take a look at here the system boundary that I mentioned to you before, and you saw that for the RFS. So the system boundary is this box here, and you can see that here I'm showing you an SMR, steam methane reformer, that uses natural gas to make hydrogen. In the system boundary, we have the natural gas extraction. You treat the natural gas, you put it into the pipeline, and then send it to your hydrogen production facility. You make your low carbon hydrogen, and then there are end users in different parts of the industry or market to buy that hydrogen from you. They may want to use that for mobility. In that case, they extra purify hydrogen, liquefy it, and send it to the end user. It may also be used in various industries like refining, cement, steel, biorefinery, or used for making ammonia. So there are a wide range of applications. And what you will do is that you stop at the gate. So they say the system boundary covers well all the way to the gate, to the plant gate, and anything downstream of the gate we are not including in our LCA calculations. And I mentioned that they have very good environmental guardrails. And as I mentioned, this is what I have been working on in the past year. So what is happening now is that if you apply these environmental guardrails, a lot of companies say it will make things more expensive, it will delay starting projects. And they say they don't care about the environment, they only think about their profits. In our company, our CEO actually used to be a faculty at Sharif University, and also he was one of the founders of the mechanical engineering department at Sharif University. So he understands the technology. He cares about the environment. So we are the only large company that is advocating to have these climate and environmental guardrails in place. We want to make sure that we get the tax credit for the real clean hydrogen that we make. And also to add, Air Products is the largest hydrogen supplier in the world. So what I did is that I teamed up with other environmentalists, such as folks in NRDC and EDF, and they also care about environment. And we have been all going to the White House together, talking to the Treasury folks, to the DOE, and explaining to them that it's important to have these climate guardrails. Happily, they listened to us, and they agreed. So we had the notice of proposed rulemaking a few weeks ago, and we saw that they included these environmental guardrails, and we have now 60 days of commenting period, and sometime in June they will finalize the Inflation Reduction Act. So hopefully, keeping our fingers crossed, these environmental guardrails will stay there as robust as they're there now. And we know other companies are going to throw a stone at these guardrails. So what are they? There are three, they call them three pillars. So one is additionality, time matching, and regionality. So additionality means if I want to make, for example, green hydrogen from electrolyzing water and splitting it into hydrogen and oxygen, What I need to do is that I have to go after solar power or wind power that was not used by anybody else before, and it's additional, it's new to the infrastructure. Time matching means that, and we have been advocating for hourly matching, means that that solar and wind power that you use should have been produced during the same hour that you make your hydrogen. And regionality means your hydrogen production facility and your renewable power generator should be within the same range in close proximity. Why are these important? Why do they help environment? Look at the impact of additionality. Imagine today's world that we don't have these new hydrogen production facilities. We have renewable power used by existing end user. In the future, if IRA is implemented without adopting the additionality, what is going to happen is that those hydrogen producers can go and take away the existing renewable power, use it to make hydrogen, collect tax credit, and then the existing end users, they still need power, right? So they will go after natural gas-based or coal-based power. So we will see an increase in the greenhouse gas emissions across the US. But if you see, if they adopt additionality, it means the hydrogen producer is responsible to go and find a new renewable energy source and leave alone the current end users with whatever renewable power they use. So that's additionality. For hourly matching versus annual matching, so we are advocating for hourly matching. If you look at the left-hand side, when you have wind or sun, you're good to go to make hydrogen. If you're at night or there is no wind and sun, what would happen is that you can't have the renewable power generation at the same time, but you can use battery storage that you have a stored renewable power in them during this, the time that you had the resources available. And you can use that to make hydrogen. What other companies are advocating for is annual matching. And they say during those times that we don't have access to the renewable power, let us go and use power from coal and natural gas. And again, that doesn't make sense because it will ramp up the production of coal power and natural gas power, and again, would increase the greenhouse gas emissions across the US. So with that being said, I would like to wrap up now. Again, as you saw, the work that I did at Professor Biswa's lab opened a lot of doors to me, and it will continue to do so. We also talked about the LCA. You saw the role that is now playing in different environmental policies. I showed you the system boundary, and you saw how it can impact the number that you calculate. The more process steps are in the system boundary, the higher the greenhouse gas emissions would become when you calculate them. And as you saw, having this LCA skill set and also having knowledge of different uh, production processes is important because it can give you a seat at the policy table. And if you're interested, you can work on making the environmental policies more robust and better. So with that being said, thank you so much, Professor Biswas, for inviting me and giving me the opportunity to talk. And I would like to open the floor for questions.
Sarah, there are indeed, I think, two questions in the chat box. Do you want to use the rest of the 5 minutes to answer them?
Definitely. So,
One question, actually.
yes. Is Air Product also working on non-CO2 GHG mitigation of the current focus is only on CO2 mitigation removal? That's a very good question. So, the current environmental policies are based on decarbonization, so reducing CO2 emissions. Uh, but also Air Products is working on technologies that help with mitigating um, other types of emissions, or you call that non-CO2 GHG mitigation. So we are working on those technologies as well. But at the moment, all the incentives you can get are based on decarbonization. So that was the answer to Ayush. Thank you for your question. And now we have a Vaishnav question. How can life cycle assessment contribute to the development of environmentally sustainable policies, um, especially considering the impact of aerosols on air quality and climate? So one of the things actually that I have been working on when I was at ExxonMobil was to advocate for having these climate policies not only based on decarbonization, but also based on like reducing everything, including the aerosols. And we know that national labs are working on that. And life cycle assessment can be used to capture and to calculate like how much of aerosol emissions that you have. There is only one caveat there. For CO2 emissions, you can aggregate them all, right? Because they all like at the end go to this into the atmosphere to the same place. But aerosols are like more local, and that's why these climate policies still have not included them. But I can see that once we get more advanced, definitely we will have climate policies on aerosols, and life cycle assessment helps with capturing those their impacts as well. Any other questions? We have 1 more minute.
Questions? Yes.
For the renewable fuel standards, you mentioned that there is a limit threshold on greenhouse gas emissions, but blending corn with gas also reduces the size of the particulates that are being formed. So they could have enhanced toxicity effects on the general population. So does RFS also consider that, or how is that navigated?
You have a very good point. Unfortunately, RFS only looks into the greenhouse gas emissions. But while shaping RFS, having those other impacts was something that they had in consideration. But at the end, they only give you the credits based on how much greenhouse gas emissions you reduce.
So was I think another question? Yeah.
Hi, thank you very much for the presentation. My name is Onochie.
Can you speak a little louder? It'll be good.
My name is Onochie. My question is basically, I'm just wondering what exactly in the process of making cellulosic biofuels that make them more environmentally friendly compared to renewable fuels. For example, does it mean that with cellulosic biomass you make more biofuels compared to making biofuel from, say, from the corn seed itself?
The main difference that you see lower greenhouse gas emissions for cellulosic biofuels compared to renewable biofuels is the land use change greenhouse gas emissions. When you make corn ethanol, your land use change greenhouse gas emissions are much higher because of those deforestation in Brazil that I explained. But for cellulosic biofuels, it's agricultural residue, so you don't see a change in the land use, and that's mainly the reason why its life cycle GHG emissions are lower than corn ethanol or renewable biofuels.
Questions? Well, then a round of applause for our speaker.
Thank you so much.
Our next speaker is Dr. Sung-Hyun Jung. He's Assistant Professor of Engineering School of Sustainable Infrastructure and Environment at the University of Florida. And her topic today is flame synthesized palladium titania catalysts for oxygen removal from carbon dioxide rich streams in oxy-combustion exhaust. Please welcome Dr. Sung-Hyun Jung.
Oh, it's not the one. Just a second. Download again. Yeah, it's here. So share the screen. It should be all set.
You can see.
This one. Sorry, you seeing that one? No?
This
Okay. Yeah. Okay, now we're good. All right, thank you. Let me hide this loading meeting control and minimize this. Okay, yeah, sure.
Thank you for a nice introduction. And I'm Sang-Yun Jung, an assistant professor in the Department of Environmental Engineering Sciences at the University of Florida, as I was introduced. And I'm really happy to be here to present my previous research, which I worked on under Dr. Bisso's guidance. And the topic is flame synthesized PD TiO2 catalyst for oxygen removal from CO2 rich system in oxy-combustion system. So the previous presentation also mentioned about oxy-combustion, but my presentation is not about the system itself, but a little bit different topic, more like application. So I will go over from nanomaterial and also theoretical approach. So as we all know, nanomaterials have been actively applied for different applications such as sensors, pharmaceuticals, catalysts, batteries, and cosmetics because of their great properties such as high reactivity and also large surface area. So far, many different the synthesizing methods have been developed with their different parameters. And those different parameters significantly affect the physical chemical properties of the nanomaterials. And here, the challenge is that for enhanced efficiency and selectivity, a close connection between synthesis, experiment, analysis, and theoretical approach is essential. So for doing that, this is my research schematics. So we develop nanomaterials using aerosol techniques, and we apply these nanomaterials for different applications. And we use theoretical approach to understand the detailed reactions on the nanomaterial surface. So using these schematics, we would like to enhance the efficiency and selectivity of nanomaterials for different applications. And here, my target is oxygen removal from oxy-combustion system, as I mentioned. So I would like to briefly introduce the background. So oxy-combustion system has been developed to enhance the combustion efficiency by using this pure oxygen. So therefore, they can achieve the CO2 concentrated stream in their exhaust, as we can see from here. And those concentrated CO2 stream can be further utilized for enhanced oil recovery or sequestration. But for doing that, there should be some requirement, like the oxygen concentration should be reduced to 100 ppmv or 10 ppmv. So in that case, we thought that we might use methane catalytic reaction to increase the oxygen concentration and decrease the CO2 concentration. So we synthesize different palladium doped TiO2 catalyst, which is really fundamental and really widely known material for the catalyst. And we use the aerosol technique. And here we specifically use flame aerosol reactor. And we introduce two different precursors. And here is brief the mechanism. So in the flame, the two precursors were decomposed first, and the TiO2 nanoparticles was formed. And then palladium clusters was nucleated on the TiO2 surface or gas phase. And then PD deposited on the TiO2 surface and then sintered to create different sizes of PD cluster or nanoparticles on the TiO2 surface. Here, we changed the PD loading. This is really fundamental and basic experiments to optimize the synthesis conditions and also identify the active phase of PD. And as I mentioned, we use the methane catalytic reaction. So we introduced 3 different gas into the system. And we introduced the catalyst into this small fixed bed reactor. And the temperature was applied from room temperature to 500 Celsius degree. And the initial, intermediate, and final products were identified using gas chromatography with thermal conductivity detector. And we expected 3 different reactions, such as the complete methane oxidation, partial methane oxidation, and dry reforming of methane. And here we can understand which one is the major reaction by comparing the reaction rate. And we changed the concentration of CO2 in the initial feed stream to investigate the effect of experimental conditions on the catalytic activity of nanomaterials. And here is our result. The first result is about the characterization of PDTiO2 nanomaterials using advanced instruments. And we found different morphology and size distribution and also the oxidation state of PD. And here there's yellow circles, and inside the yellow circle, there is brighter dots that indicates the PD. And what we found that the size of the TiO2 was not changed much, but the size of PD was increased as the PD loading was increased. And then what we found that the PD initially contains 3 different oxidation states, which are metallic PD, intermediate PD oxide, and PD oxide. And what we found that the oxidation state of PD was changed depending on the loading of PD. And this is important because it showed different activity of catalyst on oxygen remover, as we can see from here. With the PDTiO2 catalyst, we can enhance the oxygen conversion efficiency. But here, the third one, which is 0.8% PD stopped TiO2, shows the highest efficiency. And then we plotted the apparent reaction rate coefficient versus the fraction total surface area of metallic PD. And we found that there is a linear relationship between them. And this result indicates that metallic PD mainly control the oxygen removal. And then we, as I mentioned, we introduced different concentration of CO2 in the feed stream. And we found this result. And before we go into this result, we compare the reaction rate of methane and half of reaction rate of oxygen. And we found that their values are really close, which indicates that the major reaction is complete methane oxidation reaction. And then we will go to this result. And as we can see from here, the concentration of CO2 was increased. And we found that the conversions of oxygen and methane was also increased. And this is more clear when we plot between the rate of CO2 generation and the initial CO2 concentration. There is a linear relationship between them. And this result is interesting to us because the CO2 is not reactant, but it is the product. But the results show that there is some efficiency of the CO2 in the feed stream. So to understand this interesting phenomena, we thought about 2 different possible reasons, which are autocatalytic CO2 effect, and the other one is surface CO2 coverage effect. So in the case of autocatalytic effect of CO2, CO2 can be participated in both product and the reactant to generate new types of intermediates, which can reduce the activation energy barrier. And in the case of surface CO2 coverage effect, the CO2 can be absorbed on the surface and change the static structure of the surface, and then finally it can change the activation energy barrier. So the final goal of both effect is to reduce the activation energy during the reaction. And then to understand the effect of those two possible regions on our finding, we use the density function theory calculations, which is a computational quantum mechanical modeling method to investigate the electric structure of many body systems. And as I mentioned before, during our experimental findings, we found that the metallic PD plays a significant role in the oxygen removal. So we applied bulk metallic PD to create these 3-layer slab surfaces. So the bottom 2 layers were fixed and the top layer was relaxed to mimic the surface. And then we consider different absorption sites to find the optimized absorption site for different molecules. And then we investigated 2 different effects, which are autocatalytic CO2 effect and the surface CO2 coverage effect. And we started with the second effect, the surface CO2 effect. And during the experiment, I mentioned, and we found that the complete methane oxidation is the major reaction. And then it is widely known that the methane dissociation, the rate limiting step. So we started with methane dissociation with different CO2 coverage. So as you can see from here, different CO2 coverages were generated. And then we compare the activation energies with different CO2 coverage. And what we found that, as you can see from here, the activation energy of methane dissociation was decreased as the CO2 coverage was increased, which means this reaction is more favorable. And then this is consistent with our experimental findings. So we feel it might be possible reason. But we still consider the other effect as well, so which is the autocatalytic effect of CO2. So we investigated possible intermediate because of CO2. So we considered 4 different reactions and we considered different activation energy barriers. And then what we found that most reactions except this one, the activation energy is pretty high. So they are mostly like a 2 or larger than 2, which is much higher than this one. This one is around 1.3. So which means those most reactions are not favorable for this reaction. But among them, this last one shows relatively lower activation energy. So we decided that we can consider this HOCO as possible intermediate. So we investigated again the effect of HOCO coverage on methane dissociation. So we follow the same strategy which we did for the CO2 coverage effect. And then we found that, as you can see from here and here, there is no significant effect of HOCO coverage on methane dissociation. So we concluded that maybe HOCO coverage does not really affect the methane oxidation reaction. So finally, we applied this strategy to understand entire methane oxidation reaction. So we put the CO2 coverage and we also did calculations without CO2 coverage. And we found that you can see from these red lines, we found much lower activation energy with CO2 coverage. So based on these findings, I would like to wrap up my presentation. So first, we found the total surface areas of PD spaces were evaluated based on the structural properties by using advanced instruments. And second, based on our experiment and the characterization result, we concluded that metallic PD plays a significant role in the reaction. And then we found that there is a strong dependency between the CO2 concentration in the feed stream and the generation rate of CO2. And to understand this effect, this phenomena, we used the density function theory calculations, and we found that the surface CO2 coverage strongly affect the complete methane oxidation reaction. And then based on these whole findings, what we found that we have to understand the detailed reactions of the catalysts on the surface of nanomaterials and to enhance the efficiency and selectivity of the catalyst. And for doing that, we have to combine synthesis, experiment, analysis, and theoretical approach. So doing that, we can achieve the efficient and selective nanomaterials for different applications. Yep. So this is all I have for now. And thank you for your listening. And I will be happy to answer any questions.
Any questions? Yep.
So you mentioned about selectivity. So how you track the selectivity? Will it react with other molecules?
So selectivity here, I haven't tested, but I believe if we understand the maybe affinity of the material and specific product with theoretical approach, then we can understand this material can be selective for specific the product. But here in my research, I did not. Yeah, but I assume it can be.
I think there was a question there.
Yeah, thank you very much for the nice presentation. You observed that if you increase the palladium loading, you observe larger particle size and at the same time various oxidation states.
Yes.
So, and I want to ask, did increasing the loading enhance the metallic species or the other way around? And
So-
that is the case. If that is the case, can we correlate size and oxidation states?
Yeah, that's good.
Question?
Huh?
Repeat the question.
Oh, yes, yes, sure. The question is about the relationship between the loading of PD and the control of the oxidation state of PD. And my answer is yes and no. So based on my understanding so far, if I increase the PD loading, the oxidation state of PD is changed, but it does not show the increase the metallic PD. It is not. So the ratio of the PD and intermediate PD oxide and PD oxides were changed depending on PD loading, but not increasing one specific oxidation state. So that's what I found, that there is optimum PD loading to have the largest, highest oxidation state of specific the PD. So that's why I feel it is important to optimize the specific PD loading by investigating different PD loadings.
There's a question there.
So thank you for condition. Can you comment why you choose PD as the catalyst?
Yes.
For the other matter?
Sure, sure. So the question is why I choose PD, and the answer is really easy. PD is well-known material, and then I thought it will be easy, and also it will be good for me to start with PD. And then that time I used PD, and then I initially thought I will use different types of the noble metals. And then what I found this interesting phenomena, and then I continue my experiment and then other research, and then there is not much time to consider other noble metals. But I investigated different types of noble metal as well. And I found that only for this specific application, only PD shows the highest efficiency. But I just didn't have enough time why PD shows the highest efficiency. But that's what I found.
There you go. There was another question, yeah?
Yeah, thank you very much for the presentation. Considering that you found that metallic and PD was the active site for the reaction, do you think that reducing the catalyst would be helpful, and maybe that may eliminate this optimum that you have?
I think that's a good question. So the question is, if I reduce the catalyst, I can enhance the metallic PD, and then if it can be helpful to enhance the activity, I think that's the answer. Maybe also yes and no. Yes, I can enhance the total surface area of metallic PD, but at the same time, the size of PD might be changed. At the same time, the size of PiO2 can be also changed. And that this size is also important because I calculated the fraction of PD based on the size and volume and the fraction of different PD spaces. So my answer can be some amount of reduction may be helpful, but if we reduce too much, then the size of PD can be changed, maybe aggregated. Then it can reduce the activity. That's what I think so far.
Thank you so much, Dr. John. So I have a question is that kinetically, so is there going to be a predominant pathway for this oxidation reaction, or there are like a multiple kinetic pathways that are like happening simultaneously and competing with each other?
The question is about the reaction. So the reaction can be only one specific reaction, or it can be combination of different reactions. And I feel it could be. Just in my case, I found the major reaction is complete methane oxidation, but depending on the conditions and depending on the nanomaterials, I believe there should be the combination of the reactions. And in that case, we have to understand detailed reaction, the phenomena, depending on the reaction rates. But for now, my major, because the rate of the reaction of methane and the half of reaction rate of oxygen was so close. So that's why for now, I concluded that the major reaction is complete methane oxidation.
Well, I think we should move on to the next speaker. We're running out of time, but if you have questions, there's always a lunch session and discussions when you can get hold of the speaker and ask them more questions. Thank you. A round of applause for the speaker again. So our next speaker is Dr. Shalini Kavadia. She is a research scientist in the Department of Chemical, Environmental and Materials Engineering from our very own University of Miami. And her topic of the talk today is advancing material synthesis and printing technologies with aerosol-based routes. So please welcome Dr. Shalini Kavadia.
Thank you for the introduction and welcome everyone to University of Miami. I'm a research associate here. I work with Dr. Biswas, and today I'm going to present my research on advancing material synthesis and printing technologies with aerosol-based route. So Sungyun has set a nice stage for why nanomaterials are important and how the processes are important to make them efficient for different applications. But I would like to introduce a very basic example that we use every day, a paper as a material that has revolutionized the way humans communicated in early ages, and chemical pulping process is highly important to make the paper of high strength so that it's durable. So that's a very old example how material has transformed our life. And the recent example is nanomaterials that has been transforming our lives. And to emphasize the process and the fundamental phenomena involved in the process to synthesize these materials are highly crucial to give them the properties that are required for various applications. The conventional technique to synthesize these materials, especially nanomaterials, are based on wet chemical methods, which has several limitations, such as they are multi-step process, they are time-intensive, and batch processes, and also the most importantly is they lack precise control over the properties of the material. For example, if you see the 3D printing technique here is huge. It's a high-resolution powder bed fusion technique. It can print at high resolution. However, it's huge, require a spatial environment, and also can only print
Maybe that helps.
Right. So this technique can only print certain materials. So it's a limitation of material compatibility. So my research involves in developing innovative yet simple aerosol-based processes to synthesize and engineer advanced material. And I mainly focus on semiconductors, optical materials, and carbon-based materials, and thin films and structure for energy, electronics, and biomedical applications. So why aerosol-based processes? I don't think I need to mention that now, since as a few of the speakers before earlier has mentioned, but aerosol-based processes are scalable and continuous. So in my research, I start with
Yeah, if you stand here. that
just
helps.
trying to see this. Can I?
Okay.
switch
Yeah,
this?
feedback from the wall.
Okay.
So just move to the side. So,
Yeah, I just want to see the.
Oh,
no, that'll be difficult for you.
Okay.
Okay, good.
So yeah, in my research, we start with a precursor solution for of the material. We aerosolize them in the droplet. We can also start with molecules that Dr. Wujin explained. And these droplets of the materials in the solvent, including it undergoes through several reactions, several dynamics, starting from evaporation, reaction, condensation, collision, and sintering. And at the end, we get the final particles or the material of desired properties. And the properties of the material can be controlled through process parameters such as droplet size, concentration, residence time in the reactor. The particles can also be analyzed online and characterized in real time, and they can be deposited in the form of thin films or collected as powder. So several materials have been synthesized in my work, and except these two are from Dr. Okoyama's study, his work, and all of these are from our group, especially my publications. We have synthesized several with materials with unique characteristics and thin film for different applications. For this presentation, I'm going to focus and just briefly explain two types of examples. One of synthesis of oxygen deficient zinc oxide carbon dot hollow sphere for CO2 photo reduction, as several of the speakers are very interested on. We are focusing on the CO2 emission and reduction theme. And the second example is on aerosol-based 3D printing that I'm currently working on. So CO2 photo reduction or photocatalysis. So let's go through this. The first example, photocatalysis is a nice way to use the abundant solar energy to carry out a photo reaction. In CO2 photoreduction, there is a photocatalyst which absorbs the sunlight and creates an electron and hole pair. The hole oxidizes water, and the electron reduces the CO2 adsorbed on the catalyst surface. So for a good catalyst efficiency, the catalyst needs to absorb a good amount of sunlight. Secondly, it needs to have a high surface area and efficient charge separation of this electron and hole pair. However, most of the catalysts and the commercial catalysts, they only absorbs UV light, which is only 4% of the solar spectrum. And to the maximum, it can also absorb visible light if we modify them, which together UV and visible consist only 50% of the solar spectrum. So to overcome this limitation, we synthesized using aerosol-based route, we synthesized oxygen deficient zinc oxide carbon dot hollow sphere photocatalyst. So how do we do that? We start with a precursor solution of zinc nitrate and citric acid, aerosolize that into droplets. The droplet undergo through a reaction in a high temperature furnace and carried by a nitrogen gas. So the environment is inert of a nitrogen environment. As the droplet undergoes in the furnace, the solvent evaporates and the precursor decomposes. At high temperature, the zinc nitrate decomposes into zinc oxide, and the citric acid decomposition in the nitrogen environment leads to solid carbon and reducing gases. This reducing gases creates a blowing effect, pushing the material outward, creating a hollow sphere, and also result in a carbon dot. The reducing gases also reduces the zinc oxide and creates some oxygen vacancy, eventually leading a hollow sphere of zinc oxide with oxygen deficiency and carbon dot. So the important parameter here are citric acid to zinc ratio and furnace temperature. And I won't be going through details of how each of the parameter affect, but the function of citric acid is a reducing agent and a blowing agent. And you are welcome to read this paper for more detailed information. To to evaluate their photocatalytic effect activity, we use the photocatalyst loaded on a filter and supply in a photoreactor and supply a carbon dioxide CO2 stream with a saturated water. And we use different light filters to monitor their activity under different wavelength region. So is a seen in this figure, you can see, and we also compare this photocatalyst that we synthesize here to commercial photocatalyst and also zinc oxide synthesized using this method. And you can see here, these are the photocatalyst synthesized in this using this method, but at different concentrations. So these are the different parameter ratio of zinc oxide to citric acid. And you can see that this photocatalyst has a higher photocatalytic activity, which is measured in terms of CO production rate, moles of CO produced from CO2 per gram of catalyst per time. And you can see that the optimized photocatalyst with an optimized ratio of zinc oxide to citric acid has much higher activity compared to the commercial TiO2 and the zinc oxide synthesized by that, almost 12 times higher. And the reason behind the good activity of this photocatalyst are a few of them. One is enhanced light absorption. Since it's a hollow sphere, the light undergoes through multiple reflection in the hollow sphere structure. The material used is very low if it's a hollow sphere. There is efficient charge carrier transfer and improved CO2 adsorption. So we have done a detailed characterization, which you can find in this paper. And we found that because of the presence of oxygen vacancies and deposited carbon, the charge carrier separation is much more efficient. And the third region is upconverted photoluminescence of carbon dot. And I'll come to that in my next slide. So based on a detailed characterization of the photocatalyst, we proposed a working mechanism of how this catalyst work under different light region. So under the UV, and this energy level diagram is experimentally derived using a photoluminescence spectrum and UPS ultraviolet photon spectroscopy. So we draw this energy level diagram, and in the UV visible region, the zinc oxide, the oxygen deficient zinc oxide itself absorbs an UV and visible light, creating an electron and hole pair. However, in NIR region, the carbon dot absorb 2 photons of the same energy and lower energy in the NIR region, and creates and emits a high energy photon, which are then absorbed by the zinc oxide, the oxygen deficient zinc oxide. That's called the photon up conversion. And that's how the catalyst is active in the NIR region, which you can see here in the UV vis NIR or only NIR, the catalyst shows activity. However, the other commercial catalyst, they don't show any activity in NIR region. So with this, we were able to synthesize a catalyst which is active in the entire solar spectrum, UV, visible, and NIR. So let's quickly go through the second example, which I'm working on right now on aerosol-based 3D printing. As the name suggests, is aerosol. It combines an aerosol process similar what I've discussed earlier. We have a solution or suspension of the material. We aerosolize that and it combines that with the 3D printing. So the droplet goes through a diffusion dryer where we capture the solvent and the dry particles are generated. The size of the particles are controlled through the concentration of the material, and the particle goes through the customized 3D printer. The nozzle of the printer is heated at a temperature such that the particle can melt, and the molten or partially molten particle, they deposit on the printing surface and adhere and solidify. So synergy between the movement of the nozzle and the printing surface creates a layer by layer deposition of the materials and creates a 3D structure based on the 3D model that we give to the printer. We can also characterize these materials online, the particle online. The important parameters are mentioned in red here, which affects the physics involved in the process, like particle melting, particle-particle interaction or deposition, and solidification of the molten particle. And we can write a particle conservation equation, which includes a different force acting on the particle, like drag, diffusion, gravitational, and thermophoresis. So we are currently studying the particle deposition, currently studying the effect of process parameter on the printing properties such as morphology or porosity using experimental method and the computational multiphysics fluid dynamics online, so that we can combine these two and understand how the process parameter affects the properties. And I'm not going to detail mention about each of the parameter and how they affect the property, but I'm happy to discuss that offline. So this is a initial structure that we printed. We used polyethylene glycol because of its low melting point, water solubility, and because of its application in biomedical field to especially print micro devices for biomedical application. And since with this technique, we can print at high resolution, and I'm going to explain where is the resolution coming. We are mainly focusing on printing micro devices. So here you can see the square printed with this PEG, a cross section, and the top view of the edge of this square you can see here. And on the right hand side figure shows the same similar square edge, but it printed at a higher resolution. So these are at optimized condition that could print a dense structure. We could also print a porous structure with this. You can see here, this is the highest resolution the printer can print right now at 40 micrometer, but there is some overspray over here around the edge of the printed line. And this is because of the particle diffusion and the deposition. So we with the multiphysics simulation, we are right now designing the nozzle for specifically nozzle to focus this particle and print with the printer. And we are designing that in the fluid dynamic simulation, and also using that we are now have a nozzle design that we are going to print that with the 3D printing facility here at the So other than the highest resolution, good resolution with the 3D printer, we can also print a wide range of composite material by making a single solution of multiple material, or aerosolizing the multiple materials separately. So for example, here it's a composite structure of polyethylene and lignin polymer. We can introducing another stream and mixing the particles in flight. We can also synthesize a composite structure if the two materials are not soluble, so you can spray them separately. Another best advantage of this technique is you can synthesize the particle in situ using precursors. So here we are synthesizing carbon particle from lignin and introducing that into the 3D printer to print in situ synthesized carbon particle plus polymer polyethylene glycol composite, which currently no 3D printing technique can do. So this is a prototype looks like. We just filed the patent on a patent application on this different structure that we could print. We could also write on paper. You can see here lignin valorization, and these are some of the advantage. And also it's a cost effective and portable. Can take it anywhere, not like a 3D printing image that I showed on the first picture. So to summarize my talk, I showed how we can use aerosol-based processes to synthesize and materials with controlled properties. The first example was on the zinc oxide, oxygen deficient zinc oxide, carbon dot holospheres, and the second was aerosol-based 3D printing. And that is what my talk is. I would like to thank my co-author and supporter and collaborator, Dr. Biswas, Dr. Liangi Lin, and Dr. Michael Berens, and the funding agencies. Any questions?
So one question in the chat.
Here.
The second one, yeah, go down.
This one, right? Did you also study the?
Slide 5, you mentioned online characterization. What techniques are you?
On slide 5. Oh, mostly for my application, it's particle size distribution that I use SMPS or APS to get the particle size distribution. One more, right? For the 3D printing, by what
think we are-
mechanism do the particle deposit on the surface? So it's mostly impaction and thermophoresis. That's the two mechanism that it deposit on. And you could do a force balance to see which force acts on. But yeah, these are the two mechanism by which the deposition happens.
Okay, I think we're running a little short on time, so we'll move on to the next speaker. If you have any more questions, you can always get hold of the speaker during the panel discussions and the lunch, and we can continue the discussions. So with that, thank you. A round of applause for Dr. Savadia. Our next speaker is Dr. Yang Li, or Ying Li, I'm sorry. Terribly sorry. Professor Ying Li from the Department of Mechanical Engineering at Texas A&M University. And his topic today is advanced nanomaterials for catalytic carbon dioxide conversion to value-added products. With that, please welcome Dr. Yang Li.
Let me change the setting. Which one? Yeah, just a second. This one. Mhm. What do you mean? Yeah. Let me see, screen sharing has stopped. We share screen one first, and then.
Okay, you're really good to know.
Okay.
Simple things. Okay, good. You can breathe it. Okay.
It's there?
Yeah.
Are we sharing the right screen? No. Oh, sharing has failed. Yeah, should I log out and then log in again? Okay.
So for the convention.
Share screen.
So the question here is, how does my if he started, then yeah, go ahead, please. Yeah.
I think yes, it's ready. To, yeah.
Yeah, good. Okay.
So. This is a feedback from that wall. The microphone is in that direction. You want to keep it in this direction.
Move this.
Okay. Morning. First of all, it's a great honor to be here. Thank you to Dr. Wu and Dr. Biswas for the kind invitation. So today I'm going to talk about the advanced materials for catalytic carbon dioxide conversion to value-added products. Here's a excuse me. Here's an overview of my research. So I started my research on air emissions control, particularly air pollution control, from power plant coal combustion. When I started that from my PhD work in Dr. Wu's lab from University of Florida. There I developed photocatalyst materials for mercury emissions control. After that, I moved to Washington University, did my postdoc under Dr. Biswas, continued working on mercury emissions control, and then in the meantime, I started a new direction that is carbon dioxide photocatalytic conversion. Later on, I found a faculty position at University of Wisconsin, Milwaukee. I continued a photocatalytic conversion of CO2. And then after moved to Texas A&M in 2014, I extended my research to photothermochemical process at a higher temperature under concentrated sunlight for dry reforming of methane. And then also in recent probably 7-8 years, I started working on electrochemical conversion of CO2 since we have seen a significant increased installation capacity of solar panels and wind energy, particularly in Texas. So there's a good way to convert those renewable electricities and store them as a chemical fuels. Okay. Of course, I also extended my research to do some in water technologies using these advanced materials. But today I'm going to focus on the CO2 conversion. First, the electrochemical route for CO2 conversion, it's very similar to the green hydrogen production. I think Sarah mentioned that before, using an electrolyzer. So here, CO2 electrolysis actually is more challenging than water electrolysis because, as I show you in a minute, there are different pathways for CO2 reduction. And takes more energy to do that. So, but the goal of this mentioned to renewable electricity is carbon free, but the problem is the intermittent nature of solar and wind. Okay, so during the night or winter or cloudy days, but there's less is renewable, but in the very sunny days we have surplus. Okay, so a good way to store the energy besides battery is good, but besides battery is that we store the CO2 as a carbon, carbohydrate or hydrocarbon fuels as a liquid. Okay, so here then we introduce a CO2 into electrolyzer. On the cathode side, CO2 is reduced to a bunch of different products, like you see here, different depending on the potential and the number of electrons and protons available. On the other side, you oxidize water into oxygen. So then in that case, we can finish the carbon cycle and hopefully reach the carbon neutral or economy, right, in the future. All right, so then there's the fundamental challenges for CO2 reduction is that the kinetics is slow. And then there's a multiple reaction route I mentioned that cause selectivity issues. And which product do you prefer, or then you want to make a single product other than multiple products? And it also competes with the hydrogen evolution, right? For hydrogen production, competing with the CO2 reduction, and also long-term stability of the catalyst or the electrolyzer. So those are the scientific and technical issues the society is working to address. To start, I started with a CO2 conversion to CO, carbon monoxide, which is an easier pathway, only needs 2 electrons. And then because it's a gas phase, it's not in a liquid product, so it's easier to separate. And also it has it's an important feedstock to make higher carbon chain chemicals. So it's a good market there. Actually, people have done TEA analysis showing that CO is chemical environment economic. Sorry, it's viable, more viable than these other products. Okay, so here just a summary of the research I've done on the CO2 reduction from the catalytic route. We focused on the developing different catalyst materials, mainly on carbon catalyst because it's cheaper than noble or metal catalyst like platinum or silver. And some innovation on the material side is we developed single atom metal and nitrogen co-doped carbon catalyst. I'll explain that a little bit, and did various surface engineering and technology. And then lastly, we have developed some scalable synthesis for manufacturing a large quantity of catalyst. So what is a single atom catalyst? So it's different from right, nanoparticles, which is maybe millions of atoms together you form a metal particle. But in here, single atom means, as you see, it's if we have a carbon sheet or graphene as a substrate, and then for example, this red are the metal, transition metal atoms such as iron, and then the blue ones are nitrogen. So one, iron metal coordinates 4 nitrogen and then doped inside a graphene sheet. So those atoms are dispersed very well. So one metal atom is one active site. So CO2 is dropped on this metal site and then get reduced. Okay, so in this case, we have a large utilization ratio of the metals. We can save a lot of metals, right? Rather than metal particles, you're only the surface that is active. Okay, so here we started with examining different type of transition metals. We found iron and nickel are the winners with a higher CO conversion efficiency, and in terms of also low overpotential. And here to show you some STEM images of single atom, how it looks like, particularly if you look at the E and the I, those bright dots indicates single metal atoms. So we can characterize, give us the proof that these are single atom catalysts. Another method to identify is through X-ray absorption spectroscopy. Right? So we can, through the this X-ray absorption, and then they have a Fourier transform and extended X-ray fine structure. We can find the coordination distance between these two atoms. For example, do you have iron bond? So in this case, we don't see that. Only what we see is the iron nitrogen bond. Okay, that means indicate it's a single atom catalyst. And from the bond distance, also we can identify this coordination number. So we say it's iron, 1 iron coordinate with 4 nitrogen. Okay, so those are the materials characterization tools to identify single atoms. So besides those, what we're thinking, another important question for industry ask is, can you scale this up, right? We have seen these words, scalability, multiple times during today's presentation. So because to address the CO2 issue, we have billions of tons of emission of CO2, right? To convert all this into valuable products, we also need probably 1 million tons of catalyst, right? So in the research lab, typically people just make less than 1 gram per batch, right? So, but then to satisfy that, we need to make kilogram or tons of catalyst at a low cost, right? So in that case, so these are the challenges of typical traditional synthesis, use the complex procedures, high temperature pyrolysis, and then pre and post treatment steps. So those are not very scalable. What we have found recently is we can use commercial carbon nanotubes as the feedstock, right? Which has the intrinsic metal impurities of nickel iron, because in industry, when they produce carbon nanotubes, they use nickel iron as a catalyst seed to grow the carbon nanotubes, right? So then actually those are impurities that the industry doesn't want, but they're there. So, but in our case, we utilize these impurities, the waste or the unwanted byproducts, as the good thing, right? As a catalyst of transition metals. And then what we need to only is to dope nitrogen. So we find a cheap nitrogen precursor, in a simple pyrolysis process. So we found 2 methods. One is to use the CNT, put them in a wastewater containing some pharmaceuticals like SMX waste, and then the CNTs will drop these organic wastes, and then which containing nitrogen. So then we dry it and then pyrolyze at low temperature, and then we can form the single atom catalyst. The other way is to use CNT co-pyrolyze with a cheap chemical like melamine. Right, and then again, we can also achieve this single atom catalyst in a large quantity. Currently, it's supported by NSF PFI project to scale up this synthesis from a few grams per batch to over 100 grams per batch. And then we also filed a patent on this invention. From the performance, we used a flow cell other than traditional edge cell. So flow cell, in that case, as you can see on the right-hand side, you can flow CO2 on the side of the electrode, and then the CO2 will diffuse into the interface of the catalyst and electrolyte. In that case, you have a high CO2 mass transport and a high CO2 conversion rate. From the left, the two figures, we can achieve a Faraday efficiency over like 98% of CO2 to CO conversion at a range of current density from 50 to 400. Typically for industrially viable application, you want current density above 200 milliamp per centimeter square. And then the catalyst is stable for 45 hours. And then we compare with the benchmark silver nanoparticles. As you can see from the middle figure, the blue one is our catalyst. It's much more performance, higher selectivity, and also the stability. Right? And then in the meantime, the cost of our material is much cheaper, 1 magnitude cheaper than the benchmark silver catalyst. Okay. All right, so then next is, of course, we found these are good for CO. In the meanwhile, sometimes people prefer some higher multi-carbon products like ethylene and ethanol, right? We'll also look into that. We collaborate with another colleague from mechanical engineering at A&M. So we developed this advanced manufacturing of solvent-free processing. So you can see that we use commercial copper Cu nanoparticles, and then mix with PTFE, which is Teflon. Right? And then you can see we form this granular shape of particles in microsize. So it's a nanocomposite in a granular form. So then we spray these out onto the substrate, and then through a rolling, then make this electrode. Okay, so the advantage of this dry method compared with the traditionally wet air spray method as an ink spraying is that the dry method produce higher interfacial surface area and then porous. That this coating, PTFE coating, enhance the CO2 diffusion, and also it makes the catalyst hydrophobic, which is needed. And also I see you later on show you the DFT that enhance the CO2 transport from the mechanistic point of view. So again, testing the CO2 conversion performance, we found that the dry method produced higher selectivity of C2 products, 78%, right? Ethylene plus ethanol. And then if individually, ethylene is more than 40% and ethanol is more than 20%. Okay, and then there's a high C2 products versus C1 products. C1 product means mainly CO, and the ratio is 13, which means it's pretty good selectivity. So DFT calculations here showing that this Physi drop to PTFE can enhance the CC coupling to produce C2 products. Okay, so finally, maybe a couple of minutes talking about the high temperature photothermal or chemical CO2 reforming. I think previously Dr. Zhang also mentioned this dry reforming briefly as she introduced methane in there with the CO2 and O2 environment. There's probably, so in this case, dry reforming, also Sarah mentioned that, dry reforming, the LCA. So it's an alternative route for steam reforming. That's the mainstream of producing blue hydrogen from methane. The dry reforming is more appealing because it can fix the carbon dioxide, right? And then not using water, but carbon dioxide, you get more carbon credits. But the challenging is that the most difficult thing is the catalyst deactivation or coke formation, because you have CO2, not water. It's more reducing environment, so you get a carbon deposition then that deactivate the catalyst. So traditionally, people use platinum, right? So which has better coke resistance, and then nickel is preferred because it's cheaper, and the industry likes nickel better than platinum. So in our case, what our innovation is that to use solar energy, of course, first to power this the reaction, and secondly is we try to develop a unique catalyst that has both photocatalytic and thermocatalytic effects. So we carefully select the support cerium oxide, which serves as both a support for the thermocatalyst, but in the meanwhile, it is a photocatalyst. So under the sunlight, irradiation, right? Salini mentioned the photoreaction route. So the electron hole pairs generated, so then they participate in this dry reforming process. Meanwhile, PT, platinum, is a thermal catalyst for methane dissociation, but in the meantime, it's a co-catalyst for photocatalyst to enhance the electron hole separation. Of course, later on, we also tried nickel, also will work. So just here, we just showcase using PT. And then the substrate needs some promoter, like silicon or zinc. And the more interesting surface or materials engineering here is surface coating of magnesium oxide through atomic layer deposition. So atomic layer deposition is just a nanotechnology that you can deposit coating one atomic layer at a time. So you can precisely control the number of layers or the thickness of the coating. So one atomic layer is probably 1 Armstrong, so 0.1 nanometer. So we will see we can make less than 1 nanometer of coating, which shows significant effect. So we test the photocatalytic property under this simulated concentrated sunlight condition up to 30 suns. We can reach 600 degrees C or 700. Here then we test the activity of dry reforming under 30 suns or 600. So we compared the light and dark condition. In a dark condition is thermal catalyst, so no light, just use furnace to heat up the reactor to 600, right? Under light, and then it's 600 as well. So the same temperature, you can see the substantial difference between the light and dark. The hollow markers are light condition, and then the solid markers are dark conditions at the same temperature. You can see. So in particular here, the nano sub-micrometer coating of magnesium oxide has dramatic effect. So 5 layers on this right-hand side, 5 atomic layers of magnesium oxide deposition, which is it's less than 1 nanometer, can dramatically enhance the performance. So we also tested some other substrate like silicon oxide and alumina, which is non-photocatalytic. So such we don't observe these activities. That means these photocatalytic and thermocatalytic synergetic routes. Okay, so finally, I think due to time limits, I'm gonna conclude and then acknowledge my students and postdocs and also the funding agencies that support my CO2 research. Thank you.
Okay, well, maybe one question and then we'll move on to the panel discussions. Thing here.
Thank you very much for the kind presentation. I have many questions, but I'll ask one, follow up with other questions later. Let me check it. What's the preferential advantage of electrocatalyst over thermochemical catalyst?
Okay, the question is the electrochemical reaction advantages over the photothermal high temperature? Okay, so there's a pros and cons, right? So high temperature actually has higher conversion efficiency, higher conversion rate, but there's a larger capital cost to investigate, building up this, high concentrated, right, solar reactor, high capital cost, and it's also limited by, geological locations. You can only install those in a southern area where you have more, normal, irradiation of sunlight. It doesn't work in the northern area, which you barely have, normal, solar irradiation. So that's why you wouldn't see this large solar reactor, concentrated reactor in California, Nevada, or Texas, or maybe Florida, right? But then also it's weather affected. So you don't want too much clouds, then the temperature cannot reach that high. But for electrochemical, now, because I mentioned the advantages is that we have so rapidly increased installation capacity of solar and wind to generate electricity. And we cannot use all of them actually sometimes. So that's advantage. Also, that's why what I think maybe future its commercialization potential is more on the electrochemical route to utilize the low cost of renewable electricity. Actually, now it's sometimes less than the electricity generated by fossil. So it's very cost competitive, right? So, but then it's also modular. You can install them anywhere around the country, right? So that's the advantage. Of course, there's something needs to also to improve is the efficiency, right? And also how to scale them up, the reactor. But good question.
Well, I think considering the time constraints, maybe we'll just move into the panel discussions because then you can ask all the speakers the rest of your questions. You have time for that. Now we have a 3-minute research presentations. So we would kind of shorten the panel discussion now because we're running out of time. They'll start at 11:30. So we'll have a short panel discussion and then we'll start the 3-minute poster, like 3-minute research presentation. Sorry.
Yeah, so after the panel discussion finish at 11:30, we'll pick up lunch. So the lunch is ready outside. So then let's take 15 minutes to pick up our lunch and then come back. So the student presentations, so 3-minute research competition will start at 11:45.
Okay.
So those are going to be short presentations, like we just go through the research from our young talents, like the student needs. So while we're enjoying lunch.
Okay, round of applause for the speaker, for Professor Lee, and welcome all the speakers. And we have one online. I think just make sure that she's also there. I'd like to welcome all the speakers. Dr. Torkamani will join us online, and then we have Dr. Jung, Dr. Kavalia. Dr. Lee, please.
So I have joined, just wanted to check to see if you can hear me.
Yes, we can.
Wonderful, thank you.
Yeah, let me decrease the volume.
And apologies, I couldn't come in person. I wish I was there.
Okay, the floor is open. We have our speakers here and we'd like to invite all the participants to take part in the panel discussion. As Yang mentioned that 11:30 we'll pick up the food and 11:45 the 3-minute research will start. Okay. can start with the students. They always have more intriguing questions.
After a question, I saw that you, in one of the work that you work with, you converted CO2 to ethylene and all. Yes. So how do you ensure the CC coupling? Like what are parameters that are governing the CC coupling? And how do you ensure that you stop after just 2 carbons and ditching that?
Okay, the question is that.
Okay, so what was your question again? The carbon dioxide?
I can repeat. Yeah.
Okay.
Okay, so how do we ensure that the CC coupling to make C2 products, it stops at C2, ethylene or ethanol, it don't go to a higher, more, follow up sequential reaction, right? So that's a question. So actually, people are currently exploring C3 or 3 parts. It's actually more preferable if you can make C3 products like a propanol, right? Or those, it's maybe more value, higher value, but the question is that 50. So it is the more carbon, longer carbon chain is more difficult to make. So they may a catalyst is good at C3, you probably will see C1, C2, and C3, all of them. Okay, so then again, it's depending on how do you design a catalyst, right, to make a good set of 50. So it depends on the metal, the copper, for example, nanoparticle size, the exposed acids, right, crystal structure, and then surface defects, right? Also like the coating mentioned, the microenvironment at the interface of catalyst and electrode. So all these matter. So there are hundreds of research right now looking into the different issues of different materials, different selectivity. Right? So we're among one of them. So there are still a lot of work to do.
Please, yes, go ahead.
My name is Nanotechnology. This is questions to Dr. Muji. If I correctly, during your presentation, you talked about that one of the challenges for in situ characterization of the reactor is the fact that you have a high temperature, high pressure system. So currently, I just want to have an idea of what particular parameters would be very interesting for you if, let's say, you have that the ability to be able to sample your high pressure, high temperature system. This is because we have right there in the design like the high pressure, high temperature sampling, system, be able to sample at temperatures up to 1,200 degrees and pressures of up to 20. So I'm just curious as to what would be the important parameters we want to characterize at the conditions.
So the question is, high temperature, high pressure conditions, what are the different parameters that they consider for their characterizations? Is that what was the question? Okay, please.
So the industrial level of the operation, the most important keyword is safety. So actually, the high temperature and pressure is up to 100 psi. So already system reactor is existing, and then for the test purpose or improve purpose wise is realistic, very difficult because of the money wise investment is going to be huge, and then timing wise. But if there is some sampling line, what happens that in the middle of the operation, or when we take a sample from the reactor to the state port, the instrument, then definitely we should open the gate, and then there would critically impact on your operation. For example, when we open the port, then definitely there will be some pressure change, pressure drop, and then temperature will be also changing. And all those things, impact on the operation. So some of the reactor, the worst one is that silicon carbide crystal board is completely closed system and completely black box. But other reactors like FDR reactor, fluidized battery reactor, or Siemens kind of a reactor, there will be so many process transmitters. That means that we can keep monitoring that temperature, pressure continuously. But in reality, beside those two parameters, it's challenging because of the money, time, and safety. Surely, if company allows some money and then investment, then some lab scale they can start such a study. But the companies I worked for before, they didn't have so processing for them. So I hope they answered it.
So, yeah.
Yeah, so I just have a very general question. Since this is an aerosol workshop, I know you guys are working on different aspects of nanotechnology, but which part of aerosol knowledge do you think is the most important in your research, in your study? And then which part of aerosol knowledge that you're still using in your current work? Maybe one by one.
Yeah.
Yeah.
Okay. So in my, so you see the one of my slides showed you the spraying of the granules on the substrate. I think it's the aerosol, right? And then so in that work, we use the dry process rather than the wet. Of course, you have wet droplets, and then you have a problem of you have to evaporate the solvent. Right, and then your substrate may need to be heated up in industry process, but then the dry, aerosol solid particles spraying, then you avoid this solvent process. It's more environmentally friendly since you don't use solvent, and then you don't need to dry them up, so less energy. Right, so that's the part of aerosol work related. And also, I think briefly, I also studied this, nebulizer, aerosolization of nanoparticles. So if we found there's of course, the pros and cons. It's very, it's scalable, large quantity, right? But the thing is the distribution, part of the size distribution. You may not be, you don't have a mono dispersed. It's very difficult. It's also multi-dispersed. And also, are you able to generate the desired crystal face, right? Maybe sometimes it's spherical, right? But then if you want to have very defined and exposed facets, probably it's not that. You have to do post treatment probably to do those. So the wet chemistry can, method may better manipulate those characteristics. So there's a pros and cons of aerosol technology versus the traditional wet chemistry methods, but I think both we need to explore. Thank you.
Okay, so my point is where actually there is a huge difference between doing without any knowledge and do with your knowledge. Because that in industry wise, engineers mostly they do such a optimized process using a black box model. Black box model means that there will be some parameters we can tweak, and through that DOE design of the experiment, they can optimize and improve. So in my case, there are aerosol model analysis, those models starting from the molecule to particles. Then by understanding the principle, how to control the size is very critical. And then based on that analysis, you can scale up the reactor. And then always thinking of those difference, then you will understand. And those growth models is good. And second one is that particle characteristics of the particle characterizations, particle distribution and shape or surface charge, surface treatment, all those knowledges will be very helpful to controlling your functional aspects.
So for my research, I use I think I would say three aspects of aerosol. One is aerosol generation, different technologies for like atomization, nebulization, how different parameters affects the size distribution of droplets and the particles generated. And so atomization, nebulization, electrospray, these are the technologies for the aerosol generation that I have used and I utilized that in my research. The second is the aerosol dynamics. So how different forces present on the aerosols and how those forces in the reactors affect the particle formation. For example, drag force or residence time with the residence time in the reactor, thermophoresis force, impaction, so a force balance equation, and also aerosol general dynamic equation, how the size distribution evolve in the reactor, how the particle interaction happens and the size distribution evolution happens in the reactor. The third thing in the characterization, sometimes I use scattering, X-ray scattering and the light scattering characterization for this particle size and self-assembly in the particle synthesis method. So there comes the aerosol scattering concept, light scattering concepts for aerosols. So these are the concepts I guess I use in the from the aerosol field.
Yeah. Since I'm the last one, it is really hard to answer those questions because everyone already mentioned. And I strongly agree with all of these panels because I believe the fundamentals is really important because we want to control the physical chemical properties. And that is really important to get the enhance the efficiency and selectivity of the materials. So in that case, we have to understand how to control those physical chemical properties. And at the same time, our final goal is to scale up the system and then get the reproducible the nanomaterials from the industry level. So in that case, I believe we have to understand fundamental particle growth mechanisms and also how to synthesize those kind of materials. And for example, in my case, I use the flame aerosol reactor. And in that case, I can think about how the particle can be nucleated and how they can be decomposed, which depth and which height of the flame. So this kind of fundamental is needed for me to understand how to control the physical chemical properties. So, and then it is really helpful for me to decide which temperature, which height of the flame reactor, and how they can generate some kinds of the physical chemical properties. And those kind of things really helpful for me to go further to control and relate it to these kind of properties to the reactivity and the selectivity. So based on my understanding and based on our, I think, the opinion, I think the fundamental aerosol the reaction mechanisms and those kind of things is really important to understand and generate the smart nanomaterials and maybe for further scale.
Okay, I think Dr. Turkamani.
Thank you for giving me the opportunity to comment. My experience is kind of different from the other colleagues on the panel. In my first job in industry, I was working on a patented reformer, and we were trying to reduce soot. So that was an interesting experience, industrial experience, using my aerosol knowledge to reduce soot from their reactor. But after that, as I mentioned, I haven't been directly working on this topic, but I would say doing research on aerosols made me appreciate the complexity of this topic and the need to have continued research. And actually, it had turned me into an advocate for having policies that are not only looking into greenhouse gas emissions, but they also look into the aerosols and their impact, whether it's a warming impact or whether it's cooling impact. And as you know, there are like so many unknowns, and that's why we need continued research, and we need the students to continue looking into this topic to shed light on the importance of this topic. So hopefully we will have like more global policies in this area. As you know, for example, we have some like local rules, like in northern India. They wanted to battle the soot production from burning agricultural residue, and they asked the farmers and incentivized them to bring their agricultural residue to power plants to turn that into power and to be able to control and reduce the like the soot production in the area. So we have seen like local attention to this topic, but we really need like more research to bring this into like more national level policies.
The question there online in the chat. When characterizing non-spherical nanoparticles, how do you modify an analytical method? As most of these methods are instruments like SMPS, the particle sizers, DMA based, they assume spherical shape. Please go ahead and you can take turns, or whoever who wants to address that question. I think it's to everyone. That's what it says. So how do you make sure that, how do you take into account the morphology of the particles instead of just the size? I think partly you answered about the facets and things like that.
Yeah, because in my research, I didn't use SMPS to characterize the particle size. So I don't think I mean, you see the SEM, TEM, the imaging analysis, you can tell the morphology, right? So doesn't matter whether it's spherical or non-spherical. So I guess only in SMPS has that issue. I don't see there's a common issue for the other characterization techniques. That's my answer.
Anyone else wants to jump in?
I use X-ray scattering method, so we can deposit non-spherical particles on the surface and then utilize the scattering method. So you can scatter light at a particular angle and know where how the morphology based on the scattering pattern of how the particles scatter the light. So it gives a two-dimensional pattern, and to analyze that, we can actually decouple the morphology, and also with that, you could also analyze what facets and crystal plans are present at the different facets of on the different parts of the material. That specifically I use for one-dimensional structure like needles and the columns. What the morphology is. The other thing is one of my colleagues, they are developing multi-wavelength, multi-angle system so that you could X-ray scan the multi-wavelength, multi-angle sensor in the optical scattering method. So you could identify the shape of the particle. So I would suggest to talk to them. Yeah, I think they're working on that. So in real time. So X-ray scattering, you could do it in real time in aerosol form, but I have used on a surface after depositing on a surface. But with this, I guess it might be doable in real time.
Is there any more than maybe you can wrap it up a minute or two if you want to? If anyone wants to jump in, or else we will. I think we'll proceed with picking up the lunch. We'd like to thank the panel for their time and their wonderful talk.
Thanks, everyone. Have a nice day.
Thank you, Sarah.
Yeah.
Format for this 3 minutes is just they'll just go one by one and
Yeah.
just go through it quickly.
Yeah, so you're the judge.
One of them. Yeah, I don't know who the other two are.
Yeah, I think Karen Alden Dreyer, she's from Texas Tech.
Oh,
So
okay.
she will be one of them. I think maybe another one, but I don't know. Yeah, I don't know. Shruti is taking care of it.
Any idea?
Hi.
Question, how are you?
Very, very.
Nice to meet
Yeah,
you.
nice to meet you. Nice to meet you.
The PowerPoint, because I made small changes
Okay.
for tomorrow.
Yeah.
Is it okay if, like, I assume we're gonna use
Yeah.
one computer for
Yes,
it?
yes.
Do you wanna put it?
Yeah, so do you want to make more changes?
No,
Because we still have
I'll
time.
stop.
Okay.
I don't,
Okay, yeah.
you know,
If you
okay,
want more,
maybe
then,
because
because your session is tomorrow afternoon, we still
Right,
have lunch.
right. And I sort of wanted to see what they're learning, so I can make sure, you know, not to repeat and talk about
Uh-huh.
similar stuff,
Yeah.
but, okay. So I'll bring it tomorrow.
Yeah,
after.
yeah, but we already have a backup copy.
It's not good. It's already, I already changed it.
Okay.
And I put the PDF. But I
The PowerPoint.
the-
Oh, then if you have movies, then you want to also copy the movie to the.
Well, that's why I have it all here on the PowerPoint.
Okay,
So, all right, you wanna, let's take it.
yeah,
And
I
then
can.
if I make any changes,
Sure.
I'll bring a new copy tomorrow.
Sure,
But,
sure.
because I also put like thousands of backup, slide.
Uh-huh. Let's see.
It's this one,
This one,
yes.
yeah.
It's huge.
Oh, it's a huge file too?
It's a huge.
Okay.
There's a lot.
Ah.
Yeah, there's a lot of movies and a
Okay.
lot of images.
So desktop and then session 4. So right now we haven't copied the slides yet.
Okay,
So you're the
perfect. But
first
then
one. Yeah.
this one, if I'll
Uh-huh.
any changes, then I'll try not to. I'll bring it again tomorrow.
Great. Yeah, thanks again for being here, helping with the judging.
My pleasure.
Yeah. And I met your students yesterday too. So they were at the tutorial session and then chat a little bit during the happy hour. It's nice. Yeah. Yeah, so the only thing is that Cassie couldn't be here this time because she was a part of the Utah Salt Lake Dust campaign. So that campaign was delayed for 2 years because of COVID. So finally this January, the campaign can start. So yeah.
That's a bummer. I was really looking forward to meet her.
Okay.
Oh,
Yeah.
good. It transferred.
Yeah, it's there. But she specifically requests about the recording. So
Okay.
she will definitely go through recordings and then if there are any questions, I'm sure she will help.
Yeah, hopefully I'll get to see her in AMS.
Yeah, yeah.
Good, good. Hi, how are you?
Good, how are you?
Everything okay?
Yes,
Yang?
yes. So we just need the slides from Shruti for the 3-minute student research.
Should I?
Oh, yeah,
pull it?
yeah, sorry, I forgot.
The other thing is because of the rain,
Mhm.
maybe we can't put the balloon up
Yeah.
today. So they will do it
Yeah,
here.
they will bring
It's
the.
okay, right?
Yeah, yeah, yeah. So they will introduce.
And give them, when you have instrument people speaking,
So the instrument speaking, that's like 2 to 2:30, but I think that's pretty much packed.
okay.
So,
After
so
that
their
is
time
what-
slot is after the hands-on. So there's 1.5 hour hands-on.
After the
After
speaking.
that, yeah, after the speaking, and then, so hands-on finish at 4:15, and the original plan is to lead them to the,
So same time.
yeah,
But
same
here,
time.
you told them.
Yeah, I told them, Chris.
Chris and I'll tell him. So
4:15, so we're gonna divide the,
Come about half an hour before.
yeah.
And he said if the weather is weak, from out he can share it.
Or maybe leave the balloon in room and while we're taking pictures. Yeah, so we're gonna.
Oh, that's good. But maybe give them some time to speak.
Yeah.
Right?
Yeah, the tour after the hands-on, they're
Yeah,
gonna,
4:15.
yeah, 20 minutes, 20, 30 minutes.
4:15. I'll tell you.
What's the format?
Do you have the?
Audience ask questions or no?
No questions today. You
No.
will have to judge based on their performance in
Oh, so
3
there's no
minutes.
questions asking, so
No.
they just completely just go?
Yes,
Oh,
yes.
okay, so it's just for presentation.
Yeah, because tomorrow they would be
There's posters.
doing a poster, so you
people
can
can ask
have
us
ask as
questions
many
and-
questions
Oh,
as you
okay.
want.
So it's just based on presentation. That's-
Yeah, yes.
Yeah, thanks for having me.
Oh,
Good, good. How long have you been there?
This is my.
Last time I did, I think this time I was. I got.
So this I come and where were you before? Oh. You did PhD with science. I said here.
Yes, I was.
Not in Microsoft.
No, I was in public health.
Not public health. Good.
So, yeah, so I switched back to.
Very, very.
It's a tough switch.
Okay.
All right. See you. Yeah. Yeah, there's no conflict.
You're not being every day. So like, hey, I can tell you. A, people think but B, it's not your business. Your business is learning about yourself. Yeah, it's really about everything that you think that you work hard. Are you doing the same presentation you did at the one like a month ago, or did you tweak your?
So this is, so standard research, I just.
What's with your poster one? What's your poster on? I'm so excited for this presentation. Yeah, I've never seen you present on it.
Yeah, I just.
Are you gonna get started?
As soon as we get to this stuff.
Okay, yeah. There will be blood for sure. Yeah. And they have to do something. So there's various options. Right now, I should. Yeah, I want to do I'm just one long. Yeah, my mom's raising. Yeah, that's. Oh, no, crap. Yeah. Already got that.
Very much like 1,000 times. Especially like the area that where we think the same things.
I feel like you're.
You're like zero, like even like.
Yeah.
I also like, I just, 1 AM, I just go all day. Yeah, right.
Yeah. Guys, you guys haven't played that. You can like bring your girlfriend. Yeah. Maybe that's. That's so pretty.
What if we on the first or
You told the other judges that there's no questions, so it's just to be consistent.
Sorry?
When you start the.
11:45.
Oh, it's good.
Where's machine?
Oh, washing means the what?
I bought an airplane. I just bought it. Because I had it. Sorry?
You take the lunch.
So I have it once we're done.
You're speaking.
Yeah, I speak second.
Yeah.
So I just tell you, next to you.
Yeah.
So yeah, so let's leave that background. That was making yeah, so. The next three, or it's like, what's the next plan?
Yeah. For all the. The marathon Olympic process. Right? Goal of going to Stanford. Don't think about this. Yeah. Yeah, like. No. Where you're going but it's incredible. Recognize the Olympic trial. Yeah. The marathon. Yeah. So here's it. Yeah. Sometimes, but the Olympic question back.
Okay, it's starting at 50, those are about. Okay, that's good, as long as you. So you
I don't think our
nine
mind is
minutes,
going.
okay?
I think it's
And then we have 3 minutes each, but you will take some time for. Yeah, yeah, so hopefully by the month, should be done by 45. It was a chairing a committee meeting one, so I can't. No, it's online, yeah, so I just had to go back to my office.
It's not. I mean, I have a 3-minute. Well, I'm just like, I don't know, you know, all the guys, like, it's just. Then focus on the community.
Yes. The first.
In the registration, you're the first. Like, some people did not do it, so they technically picked you here first, and then I just.
My lottery was picked at the first.
Yeah.
Okay, it's probably gonna take another 10 minutes. This is my second time doing this. The fourth I did it, the secret one. Yeah, and I was creating series with everything.
Yeah, your voice was heavy.
Yeah, I was a leader.
You know what, when there was your proposal, I was in school. So I started recording and I was listening to it. And then I was just doing this, then I thought, no, I cannot miss that. When I record that, then I listen to that later. You know, that I was in shock. And also I wanted to like have a good idea because mine is also approaching. So I want to prepare myself like, so your will work as a roadmap for me.
Yeah, Dr. Wu knows everything now. Yeah, because he's on my committee, so he knows the entire process.
Yeah, because
And he's
asked
a
him
graduate program
I
director
asked
in
him,
Chile.
what are like, it's just an overall, just a written, what's the
So
component?
for like thesis proposal, you have to write a proposal.
Just a candidacy proposal. It's not a thesis.
Yeah, I mean, what you would have in your thesis. I mean, your thesis is built onto what you are writing with your proposal. So, like.
But this happens twice, right? For now, it's
No, I think
candidate trends.
I think you're talking about the qualifying.
Yeah, qualifying.
Oh, that's a difference. So that,
This must be easier. I cannot compare.
yeah, it.
For qualifying, it's just.
So yeah, for qualifying, either for our time, it was like you make your committee, they could write a question for you, and you are given 24 hours, and you have to finish each committee's question. But it could be different this time. Maybe they would ask you to present, and
Yeah,
they will.
yeah. The doctor just gave me a hint that it would be an overview. And a written report, so you need to submit a proposal, 2 pages, and then you prepare a presentation.
And based on that proposal, you will be asked, probably.
Yeah, then if you pass, then you will become a candidate.
No. Can you become a candidate when you are done with your thesis proposal?
Maybe confused. I think that thesis comes before your final, right?
Yeah, so right now I'm a candidate.
So you have become the candidate after passing that exam?
Yeah.
Which year of your PhD? It is third?
Yeah.
So you didn't give any qualifying exam?
I did give. So I gave qualifying at WashU and here also.
The same thing you did here?
Yeah. Because
you were in the middle of PhD. Some other folks were like going to graduate.
yeah,
They
so
didn't have to.
Suji, Konochi,
They didn't
their
have to.
proposal there.
So they are not doing this over here. And your PhD was transferred in a early, right? They are just.
I am just hoping the screen is, if I'm not audible, I don't know.
I have 5
Am
minutes.
I audible? Sorry.
There's not a report on the matter. They're going to have to talk about it. Whether it be, even if you're not a citizen, they just need to pay the things on it. You know, I have got to like really like debate here, and it doesn't matter.
Yeah, just waiting for one more. Sungyun is there. I will.
I will be,
So you said you were.
no, I was supposed to do that.
It's really possible.
Virtual? You want to I think going virtual.
For those drivers, they don't even actually perfect. But they're really good at it.
Things that still need to be. This will make me nervous. Yeah, of course, I mean, my first time like moving.
I love that one. Yeah, we always have
How long do you take it to set up your lab here?
I'm not a fan of us. Right.
We're using the last rough stuff. That land is more well set up. You don't need to put a tower. So when I came, it's really.
Yeah.
So that took,
Yeah, Mike. The thing is that, you know, Rogers, because really give you. You know. Which means that. Take up time, but you have to give you a review. You couldn't go up there and say, no, use that much over. Yeah.
He was better as a senator. I think he was president.
All right, good afternoon, everyone. We are just 5 minutes away from the 3-minute research competition. A few logistics for judges so that everything happens smooth and really fast. I would ask them to have a quick glance onto the grading rubric if they haven't seen that already. There is no Q&A session after the presentation, but tomorrow, all these 3-minute research are all related to the posters that are outside. So tomorrow you can grill all of us for no matter how long you want. But today it's 3-minute one and it's going to be real quick. So 3 minutes, one presenter, and we set the timer and then we again start with the next presenter. And the logistic points for presenters, your slide is already here. All you have to do is come here, say your words, and for your comfort level, I have also put the timer in front of you. So you can use that just to look at what time you are at, but at 3, as soon as the timer hits 3 minutes, you would have to cut off.
I've already done the inspection. So the way they use, I'm there. I'll be doing that. So I'll be there. 2 weeks. Get everything in the house. I'm also selling some furniture. So as much as possible, I'll be backing up.
All right. Oh, you don't need to use a pointer in this, like, yes. Okay, all right. We are starting 2 minutes before, like introduction and everything. So at 12, Washim is gonna start. So welcome everyone. Welcome to the 3-minute research competition. Something new that we introduced to the CAST workshop. Taking the AAA student chapter is organizing this competition for all the students over here. So first, let me introduce you to the judges. So we have 3 judges for this competition: Dr. Karen Erden-Dreyer, Dr. Samuel Amin, and Dr. Seungin Jung. They would be your judges. And then we have the participants, 9 participants. They would be coming in the same order as they are mentioned over here. So Washim, if you don't mind, you can come over here. So the first presentation is by Mohammed Washim, and he has the topic of evaluation of biological collection efficiency of vivas. Washim, you can start. Wait.
No, it's all.
You can start.
Hey, hi everyone. I'm Wasim, PhD student working with Dr. Wu. So to start my presentation, as you all know, the concerns regarding the spread of infectious viruses through air have been brought up globally by recent pandemics. And the collection of viable viruses is a tedious task, as most of the bioaerosol samplers inactivate a significant portion of viruses during air sampling, such as the filters, impactors, and cyclones. They have viability losses issue because of the dehydration and extraction processes, and the impinger have due to re-aerosolization. Amongst these samplers, the condensational growth tubes based vivas has emerged as a gold standard device for the viruses sampling. So in this sampler, the nano-sized particles comes in and get grown through temperature variation and water injection and turned into the micro-sized droplet, which are then collected by liquid, gentle liquid deposition. So its physical efficiency is more than 90%, and it can also conserve the virus viability 7 to 10 times higher than the impinger, but its true biological collection efficiency is unknown. And to know that, we need to find out the viable virus concentration at the inlet and outlet of the sampler. Knowing that at the outlet is easy, just doing the biological assays with the of the collected sample, but knowing that at the inlet of the sampler is hard, because we need to sample the air before the inlet of the sampler. And if we are going to do that with the help of other samplers, it doesn't work because other samplers have viability loss issues. So in this study, our proposed method is to connect two samplers in a series, and then the viable collection from the one sampler adjusted by its physical efficiency will help us to determine the viable virus concentration at the second. And comparing the inlet and outlet, we can drive the biological efficiency. And once it's known, it will be helpful to calibrate the other bioaerosol samplers with our gold standard device. So in conclusion, the main focus of my research is the improvement of technology for maintaining the viability of viruses during the air sampling, and also determining the accurate infectious virus concentration from the environment, so that we can measure the degree of threat during any airborne transmission of infectious viruses, and we can prepare ourselves from any further epidemic. Thank you so much. There you go.
Thank you, Washim. All right. Next is I am myself. So I would be talking about the unknown potential of bioaerosols from wastewater treatment plant. So as soon as you hear the word wastewater treatment plant, the first thing that comes to your mind is yucks. But there's a hidden potential that could help us find out the emerging airborne pathogens, associated mutations, and that would eventually help us with better public health policies and climate change. So at a wastewater treatment plant, because of bubbling and how the water enters into the wastewater treatment plant, many aerosols are generated because of the wave breaking and bubbling mechanism. So in order to look at how the bioaerosols look like, we sample those aerosols from the wastewater treatment plant. And then in order to find out what is the exact composition of those aerosols associated, we deploy the whole genome sequencing of those samples. So now you might be asking why whole genome sequencing is required. So obviously we can do the targeted approach in order to look for the viruses that are present. But if there's something new, which is unknown, targeted PCR would not tell you about that. For that, you need to do the whole genome sequencing. From there, you get to know what are the different genes, what are the associated mutations that you can look around. And why that has become much more prominent these years is that we all got to know about COVID-19 pandemic, but it was not just one SARS-CoV-2 variant. We had variants coming after. The same thing could be happening with other mutations which we are not aware about. The other concern which we all raise is that once the wastewater treatment plant treats the water, that water goes back to the ocean. And let's say if we don't have the if the pathogen that is present in the wastewater, if that does not treat itself, it would be leaked into the treated wastewater, and then it spread across the entire ocean. And that is where we need to look for the public health safety, and that is why we are moving towards looking at the whole genome sequencing of the bioaerosol emissions that could help us give better potential of the bioaerosols and what are their impacts. Thank you. You can start.
How was your summer?
I'm sure many of you may not want to remember it because it was hottest summer of the recorded history. On one hand, we have climate challenges such as global warming due to excessive use of fossil resources. On the other hand, we have burden to take care of our rapidly growing population. One potential solution to address both problems simultaneously is to decrease our reliance on fossil fuel resources and start increasing the use of waste and sustainable materials. Nearly all industries generate some form of waste, such as paper and ethanol industries, where biomass is used as a feedstock. A material known as lignin is generated as a waste byproduct. Staggering 100 million tons of lignin is generated every year. To put it in perspective, this amount would fill nearly 500 billion oil drums every year. Unfortunately, most of this lignin is just burned due to lack of alternative applications. Now imagine a world where this 100 million tons of lignin is not burned, but transformed into a material that can be used into batteries of electric cars. Well, my research shows the way to achieve this transformation efficiently. I'm using spray-based aerosol techniques. In this technique, I dissolve the lignin in a solution, and the lignin solution is spread into fine droplets. The droplets are then sent through heated tubes where they undergo a process known as pyrolysis. The emission of gaseous products due to pyrolysis leads to synthesis of porous particles from this lignin. The most important property of porous particles is the surface area because their energy storage capacity is proportional to their surface area. The particles I synthesize are 1,000 times smaller than the thickness of this hair and have extremely large number of small pores. As a result, if I just take 10 grams of particle and spray it into a thin sheet, they will occupy a whole soccer field. Not to mention they show excellent energy storage capacity. This technique, it's simple, it's rapid as it takes only order of 10 seconds. And it only requires water and lignin as a precursor, so it's environmentally benign. This is a significant advancement for scalable valorization of lignin. As a human beings, it is our responsibility to leave our planet for our future generations in a better state than we inherited it. Taking care of waste is certainly one step towards that. So let's use lignin for fueling future, not the flames. Thank you.
Thank you. Next, we have Chanakya for particle formation and plasma-assisted combustion. Let's start.
Yes. Climate change is the biggest challenge that humanity has faced, and the reason for it is our reliance on fossil fuels and the emissions that we put out. And it has been, it is known to increase warming, cause public health concerns, and also at the same time, limit our ability to understand the climate around us. And the smoke and other aerosols that we emit, on top of being undesirable, it is generated from flames. But at the same time, flames are known to be very reliable sources of generating nanomaterials, which hold a lot of promise. Now, as we are transitioning towards more greener fuel sources, we are swaying away from fossil fuel sources, but we still need nanomaterials for our future. So how do we make it more green? And can we make it more green? Yes. And one of the answers is plasma-assisted combustion. The way that we make it green is by introducing plasmas. And what is plasma? Is basically a fourth state of matter in which it is mainly consisting of ions. So when we provide enough energy to a gas, we strip off the electrons from atoms and molecules and create a conducting channel, which is called the plasma. Now, when we introduce the plasma into the combustion, it has been shown that it would increase the stability of the flame and also at the same time enhance its efficiency, which means that we can run the flame at with much lower fuel content, and we can at the same time extract more energy per unit mass of fuel.
Now that is plasma-assisted combustion. Traditional combustion, which has been used to generate nanomaterials, it has been studied for a long time. And we know the steps that particles take from products all the way to the final, from initial nucleates all the way to the final products. And because this process involves chemical reactions, there is a crucial role that ions and charges play at every step of the process. Now, because we introduce plasmas into the system, we have a very highly charged atmosphere in which the high energy electrons, which are 100 times more energetic and 1,000,000 times more dense in electrons, they influence this process. And because of this atmosphere, the process is very different. Now, the process is attributed to three effects: kinetic, thermal, and hydrodynamic. And it is difficult to understand this mechanism because all three products are because all three processes are involved. Now, in my research, I'm isolating each and individual process and optimizing the particle formation. Now, with such a mechanistic understanding, we should be able to understand, optimize nanomaterial production, and at the same time move towards a sustainable future. Thank you.
Thank you. Next, we have Noyon on influence of rainfall on bioaerosols.
After the rain, we can see the clear sky. We can see the clear sky. Yeah, most of the particle, such as the dust, heavy metal, sea salt, or a mixture of them, are mostly washed out after the rain. How about the microbes? You can see the mold in your wall, or your food is gone bad quickly after the rain. That can be caused by bioaerosol. So even though the importance of the bioaerosol study, most of the studies are focused on the soil or water because the air has much lower concentration of the microbes. However, it is important. We breathe in air every day. We breathe in about 7,000 liters of air every day, which is 2,000 times higher volume than our daily water intake. Moreover, the size of the bioaerosol is matter in terms of the transmission and absorption in our respiratory system. Small particles penetrate deeply in our body. Also, the small particle can stay longer in atmosphere than large particle. However, despite of the importance of the bioaerosol study with the size information, most of the studies focus on the bulk aerosol sampling because of the low concentration. Some studies are focusing on the large particle because they can increase the mass concentration by focusing the large particle. In my research, we got the sample from the different size range of the bioaerosol from the less than 1 micrometer to the larger than 2.5 micrometer. For brief result of my research is in the bottom right figure. So you can see the diversity change before, during, and after the rain. And the color represents to the size. Blue is the less than 1 micrometer, and black is the larger than 2.5 micrometer. So over the time, the black dot is gradually decreased before, during, and after the rain. While the small particle less than 1 micrometer is stable, their diversity during and after the rain, which means the different size of the bioaerosol react differently on the rainfall. For the more detailed information is in the poster session. Thank you for your attention.
Thank you. Next, we have Marcus.
Start.
Should I start?
Yeah. Hi, everyone. Today I'm talking about an important process in the atmosphere that is new particle formation. We all heard about aerosols and how they contribute to different aspects. So studies have found so far that atmospheric aerosol load is contributed by new particle formation. And what is this process? Is two-stage process. The first one is the formation of thermodynamically stable clusters, and then the subsequent growth of these particles. And why does they matter? Is because these new particles, they are formed in the atmosphere, they contribute to the cloud aspects and the cloud properties. And when we have thicker clouds, they can contribute to the planetary albedo and also contribute to the understanding of our climate nowadays, and then trying to project the future climates. So far, we have identified some aspects that influence this new particle formation. Some of these aspects are related to the precipitation, the presence of precursor gases, and also the cloud aspects. First, talking about the precipitation, we're working with data from the some DOE campaigns. And then in one of them, we identified, for example, 50 cases of new particle formation, and 62% of them were after precipitation cold front systems. And then this might have influenced how the wet removal after precipitation can remove larger particles existing in the atmosphere and then promote conditions for new particles to be formed. And also we have identified that around 68% of the new particle formation were happening in these scattered cloud structures, that when we have spaces between clouds and we have available spaces for thermal radiation from the sun to be hitting the surface and then promote those photochemical reactions to form new particles in the atmosphere. We have still ongoing projects is identifying how those new particles formed in the atmosphere, they contribute to the cloud. It's an ongoing process, but we hope that with the new knowledge that we aim to find, we can understand more of this climate and future climates. Thank you.
Thank you, Marcus. Next, we have Onochi. He would be talking about aerosol technology for carbon dioxide capture and utilization. Let me know when to start.
Climate change is real. The major reason for this is anthropogenic CO2 emissions to drive global energy. The world population is expected to grow from 8 billion today to about 9.2 billion by 2040. The amount of people living in urban areas is expected to increase from 56% today to about 66% by 2040. What is the implication? More demand for energy. If we continue to produce energy in the way we do today, by 2060, it has been predicted that 60% of Miami will be below sea level. Cities like Lagos and Miami are in danger. And my thesis is focused on developing aerosol technology to tackle this problem. And you may begin to wonder, how can aerosol technology enable carbon dioxide capture? It's simple. We have identified pressurized fossil combustion as a process that can enable the combustion of biomass, preferably, and also fossil fuels to develop energy. Pressurized fossil combustion has been shown to provide 15% more energy per pound of fuel. This is largely because of the capture of the end of condensation of water at high pressure. I have designed a pressurized drug-tip furnace to enable the study of how particles form at pressurized conditions. This understanding will enable us to guide the development of the pressurized combustor to either suppress particle formation or enable particle formation at a size range that is easy to capture using conventional capture devices like the ESC. The second part of my thesis is focused on developing aerosol technology for carbon utilization. How do we do this? We generate several advanced nanostructures in flames. So by tuning the flame structure, I am able to develop several nanostructures that can be used as catalysts. These catalysts enable the conversion of carbon dioxide into synthesis gas or dimethyl ether. And these products enable us to produce sustainable aviation fuel, sustainable fuels for marine and for trucks. This way, aerosol technology is contributing to ensure that we have a sustainable future. Thank you.
Thank you, Onochi. Next we have Yiming. Yiming, I'll take care of that. I'll take it. No, you can leave it.
Yes.
Let me know when to start.
Yeah, please start. Thank you. Hello, everyone. So my research topic is about the crumpling of the graphene oxide to make cancer treatment drug delivery systems. As you can see in as you know that cancer is a major threat to human health, and nowadays a lot of research has been focusing on solving this problem. There are drugs being developed, and those drugs can be applied in those like chemotherapies. But as you all know that, so if you use chemotherapy, it is trying to inject the drug directly to the human body, which causes a lot of damage to the healthy cells. This is also why it's like a chemotherapy is not such like a good way to deliver the drug. Here, so we develop a drug delivery system which act as like a package, as you can imagine that you receive a package from Amazon, and then you open the package and then you get your effective product. This is the same case. So I use graphene oxide to load the drug and then deliver that to the tumor site. But using the graphene oxide has several problems. One major problem is that due to the structural property of the graphene oxide, these graphene oxide sheets tend to aggregate each other due to the forces between the graphene oxide layers, as you can see in the first picture. The way to solve this problem is trying to crumple this sheet graphene oxide structure using this furnace aerosol reactor. So this is an aerosol approach to convert the sheet-like structure to the crumpled ball-like structure. In this ball-like structure, we can reduce those interactions between those graphene oxide layers. Then, after we have got these composite structures, we are able to modify those surfaces and attach those drugs on those crumpled structures. This will make this drug delivery system has a higher loading value for the drug, which makes it a better and a more competent system for treating cancer. Thank you, everyone.
Thank you, Yiming. Last presentation for the competition. The speaker is Shahar, and she would be speaking about air pollutants from sargassum stranding.
All right. I want you all to close your eyes and imagine that, close your eyes. Imagine you're at the beach here in South Florida listen to the waves. You're relaxed, you take a big breath in and hold up. What is that smell? If you're from South Florida, you might have noticed an odor at the beach from sargassum stranding. And if you're not from Florida, or maybe you are, but you've never heard this word sargassum, sargassum is a type of macroalgae that in recent years has been washing up in beaches in the Atlantic and the Caribbean. You might be wondering, why does this matter? And I hope that in this presentation, I can explain to you why sargassum stranding matters and why you should care about it and what we're doing to find out more. So sargassum, as it breaks down, has effects that reach into both the health sphere as well as the climate sphere. Health-wise, sargassum, as it decomposes, releases hydrogen sulfide. This is a gas that can cause headaches, and it can also cause respiratory symptoms. In fact, in certain islands in the Caribbean, there's a noted increase in how often people have to go to the doctor around times when large amounts of sargassum wash up because of headaches, because they have trouble breathing. So it's dangerous health-wise. And in addition, we care about bioaerosols from the sargassum, right? There's all this bacteria in the water. There's all this bacteria in the algae. When we have it wash up in large amounts, there's concern, right? We don't know what we're breathing in when we're at the beach. Another aspect that's really important and we're curious about here is the climate aspect. So as the sargassum decomposes, it emits beyond hydrogen sulfide, other sulfur compounds. Some of these compounds are crucial to the formation of cloud condensation nuclei. These play a big role in the albedo effect. So understanding this role better is crucial for climate scientists who need to understand our planet's carbon budget. So just by studying this algae, we get a better sense of this one piece of the picture that plays a role in climate change. Combined, all of these things enable us to understand the effects, not just on South Florida, but on all of the regions affected by sargassum stranding. Right now, we're in the middle of a 2-year project involving fieldwork and lab work to study sargassum as it decomposes in both the lab and in situ. So that when South Florida residents and people all over go to the beach and they take that deep breath in, they know exactly what's going on. Thank you.
All right, with that, we end the presentation, all the presentations. With that, I would want to thank the judges. Thank you so much for your time. We did finish that in 30 minutes. And thank you all for coming here, listening to all the presenters over here. Tomorrow, please don't forget to take the opportunity to grill us. We are ready for that. Thank you all.
So I also want to briefly mention that at 2, we'll have the hands-on instrumentation session. So the session will first start in this room here, where our industrial sponsors will first give 5 to 7 minutes about their instruments, their applications. And then after that introduction, we'll move upstairs to the 3rd floor to the lab session, where you can have real hands-on experience. All right, so I'll see you all at 2 p.m.
And also lights for
I mean, yes, or you can say no one slide, you can also. And then after that, and then after that, they're all upstairs, invite to go to 15 as it goes 12, yes, on the hips. Yeah. Do you want to upload some slides? First. Yeah, you can still get it. I'll put it here. You want to do that? Yeah, it's fine. Go upstairs in order to do that. Okay, okay. Yeah, just send me an email. Okay. I'm young. Okay. We're in contact about the lab demo. So send that to me. Yeah.
Do you need any help?
Yeah. Oh, I was like you over there. Yeah, yours.
Yeah.
This looks like, when I looked again, I'm like,
You guys are, yeah, practice, but I was like, working on block, like, money. Yeah, yeah, it is. Yeah, I think what helps, like, whenever I'm doing practice and you mess up. Yeah, because I used to be a sort of person who practice and I could be on slide 11 and then slide college. Like, but then you don't actually do that. Yeah, but I don't mind.
Direction on stuff, really, it'd be cool to see the parents, but I know that, I know that.
Stress, I think it's not.
It's what I don't have.
My work people, but I love like public speaking, like people that mention. You know, it's 3 minutes for everyone, that's like, yeah, meeting. I don't. It's a bragging. I was the last one who's on Slack. We got everybody at visual. Yeah. But I wish I like, I was, this is like, I process the thing quietly. But it feels really different to like then be. I should go back to when I was really young. Present this recently, because I was like, start making that and sit down and be like, I have a group presentation and laugh. It's just like it's easier to relax, you know, like I was able to read my
I think I changed because this thing.
李老师，这个我干嘛？
叫我加一个。This is my. But I like that this is like, that's normal. I don't know, you know what, sometimes you experiment, but I would. Based on experience. Especially empirical. I went to school, and I don't know if this is actually a formal part. You know, the US has school curriculum of schools that offer a course that's like very advanced. There's advanced placement, and there's IBs and it's based off of the British system should be called British high school students do their GCSE like IBs and so you choose certain subjects and you take exams for those subjects, and there's a certain number of points and you have to add up, you know, some you choose to like really specialize in, some you get lots of it. But it's international standardized, it's obviously and maybe it's like, you know, like it's English literature, you can take it it's based off of the pavement groups, sequence rules, rated for something yeah, but like, I don't know if this is actually the Roxy, there was some things that we had a thing like we were really encouraged, we were capturing the audience that we have to have 25 or so minutes. Yeah, so like you could have just give a presentation in the middle, you know, ask a question, raise your hand. I did all that. It was supposed to be very dry, very precise, definitely not. Like, I like seeing people's perceptions and seeing what people think. The graphics that people have. I think there's like, I think that there's a lot. It's like the way they go that James, you know, it's weird. It's like, yes, we can be private. There's room for it, but like this, you know, I get the need for numbers, I get the need. Yeah. So he wasn't doing that to so whenever also take for that.
哦，那个他
然后还有我改的
Yeah.
Sad because it's really so and I've heard like people talk about how like people say yeah, the state it wasn't The job stability. I get, yeah, investors. They're focused on I will get their life, they don't wanna help find another job and start off again. But it's sad that teaching is really undervalued and like, you know, a lot of the schools where teaching is really valued. They don't have something. I think it's sad. It doesn't seem like there's a lot of it feels like it's that way in a lot of the theaters where people say they got and then turn it into they'll try to value other people.
正好这个东西就是移动然后做从左转啊，就放在这里面，就稍微我比较想的是回国当
They managed to give even the less focused you see industry like that will aid institute and some of that is money. It's a good the frustrating thing for a lot of people. If you're in the profit, it's not 100% of your classes, you're here in the acceptance and state. But they so you might be you're in the class, you might just those are and then like we get into you see the other side, which is not a bad student, but like for some people they want something. There's not a scarcity reason. And
我觉得是能够哎呀，真的把这个读出来，我觉得不容易。
It's not like when they don't. It's the statistic of what is that? So. A lot of this, you can Yeah, it's sad because it's like oh my God. I think did I tell you about how people was a doctor? Right? Brother. It was fun. And my dad's supervisor, he was doing this and technologist. And so it was 15 minutes late, because it was 15 minutes late. My dad. And supervisor. He got a job where my mom. Yes. Yes. Yeah. But then, 我是觉得 reference to me, 50%, 然后这个然后第这个是俄州高三的每次的高三在这个 然后这个在我对这个还是很有对的知识，这样子。然后就是我在用那个行政上的去弄另外一个这个是这个也是真实的阐述的。也在这里，剩下的一个三层，然后加上还有预测到被线，因为他们的预测这么多它的相关性，然后反正我觉得也好吧，也好。但是如果说我们一直在那里换了几些什么，还有一些而且就是像很多超商粉，它在启动就是我的想法是，我可能会因为我们就跟进我或者自信成长你通过以往的到第三代的点是什么？然后达到那个above the level of safety,因为很多国家的它但是你要不测的话，不测你这样的话，不知道我的这个
one of them has like a fish, and the other one is like which is the water money to the lake, which is the water money. Okay, so like okay, so it's not segregated because we're not even just do according to the plan, but it's like it's an incredible amount of yellow, especially when you're like the 22 is like 66. Like benefits that you get. In inside some have really small freaks.然后看看这个人分公司大概差不多。现在跟上用户多少特别多少look at appealing to places that are many different the place I did it out they were big 他们推广用户来吧他们没有I don't think any of them really have to they did. They rarely use it. 他们这样，他们 free code people interaction and then in exchange 因为真的好，有一些虽然换的话，他们真的可以然后呢 field 然后 field 非常细，然后这个 make 的成成 post So long term evaluations for programs and a lot of our I did it especially post operation 这样的东西就是没有找到，你可以找到你的意思是放了many hours 就这样，所以他们有一个近自然2-3年1年了，他给你继续推出比较我们是3个月或者到I didn't set out one time. I didn't know that. I didn't know but it's我只拿machine learning for test 没拿来什么PM 这种总的来说感觉来有相对有用的还比 sensor 要稳定。是的，所以很可能可以看看这个什么比较，而且你可以除了 R square 还可以看 bias， conventional
哦，OK，我当初这个时候就感觉是我这个没有看到，我就加了点那个。我觉得，对，我就觉得这个是不是很错？这个我现在那个想法全没有。而且我没有看见过有个运动的大部分。我只能把它这个 data， I got so many people never know that。反正我就多做过，我让他的运动在本身这个词本身就讲到 science， 因为你是对吧？这个是我觉得compare 一下这种 model 来单体上，我拿这个model， 然后再 compare 一下。我们这种可以，就是这个。是不是看到这个无论把它用people还是那个我一直想用，但我一直没有理错。所以我觉得所以我现在对，所以我觉得 PM 在做一部分。Did it all go good? I think so. When I looked at the side of the nitrogen, like I could go from every single thing. I lived and started it's like a mile. I mean, there's no background. I was hoping they just I was like, there's so much.
So when should I be?
Yes,
That is when it starts.
Yes, that's I would show you there. There's church. So I try to.
Yes.
Right.
So I need to moderate just for.
It's really nice. I'm getting still like the work to use on that.
Okay, okay.
There's a small I'm not actually before it's and then you go into
So I gave the scoring score sheet Dr. Bags. I haven't done that because I'm also your yeah. So I just gave it to Dr. Bag. So you are Dr. Bag, you have to go through.
That's it rains. It's Yeah, that's what I do. I really wanted to do a study of product. We didn't have that many. There were programs that really use that by completely free. And I have a really good friend did study and the program was actually so I was like, oh, I think about it as a whole way, like but it seems like nothing in place. There's a rise in a lot of people. It's not really but like there's been a big thing they seem to know that's yeah.
박사 3년 차인데 아,
Yeah. Yes. Yeah, thank you for facilitating it. You're done, you're like, oh, great. Thank you so much. No more speakers. We're just doing the whole video. So, is it just good until we get the judge? Yeah, I think so. So it's like the judges, if you poster, there's criteria that's judging on the criteria was set. And they're just looking for those things.
Leading by industrial safety.
except you get to learn right.
Yeah.
We're gonna do it, we're gonna connect it to the laptop, and if we can make it work, we swap the camera with that, we don't have to do that. But with the lag, if you have the data, you turn the laptop and you can see it's working and you do it. No, it's not, but if you have the streaming data on the software, you can see numbers. For them, it's very consumed data, they can. It's good to both, but if we can get it to work connected, I know we install the software, and everything, so if we can install the software, so if we can make it work, it's the team can actually click at the right place to show that there's data coming, then we swap, it's already working, doesn't have it's working.
We still have 45 minutes.
Yeah, no, it's this.
What？没事，你就算了，要不就在这儿搞还是
What？
我想处理一点事儿。
Okay.
Everyone, do you have the laptop to connect to the grid? To set up?
They have it.
They have it?
They have it.
And also, where's the table to instrument demo?
It's upstairs in the lab. It's the lab.
Or maybe a little lemon green.
I didn't
Yeah,
have a
I
chance to watch that.
Yeah. No, 17. Oh my God. And she
Yeah.
Yes, we did not miss it, but I was like every time after that we had to go somewhere, I was like, read me that. Because not everyone.
Thanks. Over here.
So go down to C, it's out, there's a cast.
Oh,
There you go. And then I've got a little 5 to 7 minute intro.
Okay, great. All right, so in terms of sequence, what about we just go this way? So
Yeah.
we're not confused.
I can figure it out, it doesn't matter.
Yeah, so we'll be the third thing.
I will come when I'm called.
Okay. Yeah, all right. Thanks.
So let me copy it over here.
I guess the
Make it sunset. Okay.
All right. So
And then,
yeah, hit eject. I want to
this,
damage
yeah,
here.
yeah. Okay. Great.
Perfect.
Good job.
All right. No worries.
But like you have to, but it's just like that's what everyone I think is so easy. I study that. So the name of the degree is private products and private. I think that's how you make it. The department rebranded many departments in years, but it used to be emphasized in environment. A lot of it. Design, yeah, very important, but we designed an aerobic. Yeah, we also have the biggest difference is that we were on cells on campus. They were out in the land, they go on land, so they go on that universities started putting on land, even hours. Once in shall we it's a restaurant like a lot of people. The extension program despite seeing how they were get through in the States, see how they were fitting. They also have a lot of people it's sexy and like learn the skills. You know, that's something that people say somewhere that's how you're yeah, you look on the map. It's also big. You look on the map. It makes me sad. It makes my ear. There's no way. I really want to go to those lists. I wish there was like a aerosol. You got to go back and really excited. It's where you know what? Yeah, you know where Lego is. Yeah, and that was like it was I was sort of yeah, it's really the only place I've been. Oh, where did you go? I wish. Oh my God. Honestly. I'm excited. How are you getting there? Okay, right. You can also do handcraft, which is way cheaper. Handcraft is the train, so bright light. So bright light started last year. Handcraft has been around. I'll say this, handcraft is much lower. It's about half the cost. So like round trip on handcraft, what it costs about bright light. The bright light is way nicer. And you know, either one is going to. I think it's 160 pounds for the bright light. Not like so cheap, but cheaper than the light. My poster was the no, I was just like, I really like I love it. My poster, but I was like, I couldn't say anything about it. Do you want me to print them?
Hey, hello everyone. Welcome back. So now we're going to start the session 2 of this workshop, which is the particle instrument hand-on demonstration, right? So the way we operate this session is that we'll first have a half an hour kind of quick go through and then the slides introduction from our like industrial sponsors regarding their instruments and also the applications. And then after that, all of us will go to the third floor where they already set up these instrumentations where we can go through them one by one and then have more in-depth conversation with these companies, right? So we'll first go through these slides and then we'll go according to the sequence on the screen here. So first is going to be TSI, and I think Cherie is going to give a short introduction. Okay. Yeah, sure.
Good afternoon. My name is Sherry Elsie with TSI. I'm going to give you a quick background on our company and then highlight the instruments we have for aerosol measurements.
We're not muted, right? Oh, we're not. Okay.
Oh, could you not hear me?
We're good.
It's working. Yeah. Okay. So TSI was founded in 1961 by 5 researchers at the University of Minnesota. And today we have over 900 employees worldwide. Roughly half of those work at the headquarters, which is Shoreview, Minnesota, in the Twin Cities. And then we also have offices throughout the world in several other locations. TSI has many different divisions, and so collectively we have more than 200 measurement instruments. And this is just showing you some of the main applications that we sell into. But more relevant for this workshop, the area that I work in and that my colleague Andrea works in is called particle instruments. And so that includes these categories of filter testers, aerosol generators, particle counters, sizers, and those accessories. And so some of those key applications are indoor-outdoor air quality, ambient research, combustion emissions monitoring, filter testing, and inhalation drug development. That's not exhaustive, but those are just some of the main ones. Our automated filter testers are kind of unique because they are primarily sold into industry. So companies that make filters or filter media. These are all-in-one turnkey solutions. So they include the generator and detector and all the flow control and everything. And they provide the filtration efficiency measurement. We do also sell these sometimes to academic labs. We have a version that's used for QC, one that's more for production lines that run 24/7, and then one that measures filtration efficiency based on particle size that is used more for R&D purposes. But the rest of the instruments that we have are sold as individual components. And so then researchers have the flexibility to kind of pick and choose, combine different generators, detectors, and sizers. So we have a variety of different aerosol generators. They can generate particles as small as 2 nanometers and up. Our counters can measure from 1 nanometer and up. And our sizers can also measure from 1 nanometer up to 20 micrometers. And then we have accessories that go along with that. So if we look at each of these categories in a little more detail, we have generators that can take dry powders and make them airborne. So this is pretty much any material in dry form, as long as it's not super sticky. And then we have a few different options based on what size range, what concentration output you want. We also have some generators that can take liquid samples. So this is if you dissolve material in liquid or if you have solid particles that are suspended in liquid. And then there are some that can generate a polydisperse aerosol, nano sizes or super micron sizes. Others can generate a very monodisperse aerosol, again, in the nano range or in the super micron range. And also this is just dependent what size range you're looking for, what type of material you have, what kind of concentration you want, and so forth. And I know you can't see all these numbers up here, but that's fine. But we have a range of particle counters. And there are so many different because there are these different capabilities that people care about when they're looking for a detector. So we have a small handheld particle counter that you can just walk around with. And that's used a lot in industrial hygiene, occupational settings. People just want to quickly identify where is an emission source coming from. And then we have butanol-based and water-based benchtop particle counters. And you'll see one of the water-based counters in the demo today. For sizers, we have a variety that can do supermicron sizing and submicron sizing. We have one based on aerodynamic operating principle, and that's used a lot in looking at bioaerosols and just how particles are transported through the air. So a lot of climate research. We have an optical particle sizer. We have one that's more unique is the QCM Moody. So that's a quartz crystal microbalance Moody. So the impaction stages are quartz crystal microbalances, and that lets you get mass in real time. So this is a first principles mass measurement. So you can use that to look at mass up to 2.5 micron. And people are also interested in it as a reference device for low-cost sensors. As many of you know, low-cost sensors aren't necessarily consistent from one to another or highly accurate. And so this is a way to compare them to a direct measurement. And then we have electrical mobility-based particle sizers to look below 1 nanometer. We have one that's very high resolution. We have one that's smaller and more portable, and one that can do super fast measurements. And then for offline analysis, we have some cascade impactors. There are some that are designed for personal sampling. So the mini Moody's can actually be worn and people can walk around and sample with them. We have others that are designed more for ambient monitoring where the stages rotate so you get uniform material collection. And then we have some that are very high flow rates, targeting more the really clean environments where your concentrations are going to be low. And often people need to somehow condition or control their aerosol as part of your research or as it's necessary to get it into the instruments. So we have some accessories for drying or diluting or neutralizing the particles or in some other way shaping the aerosol distribution. So thank you for your attention and for the opportunity to be here. I know I went through a lot of material pretty quickly, but just wanted to give you an overview. And Andre and I will be here today and this evening if you have other questions. I will also have this up at our demo session. So if you want to scan that QR code, and then you can see the full particle instrument catalog. Thank you.
Okay, so our next speaker is going to be Braden from Handix.
Oops, sorry. Hi, everybody. My name is Braden Stump from Handix Scientific, and today I'm here to talk about an overview of our company as well as the instrumentation that we offer. Thank you. So Handix Scientific in its current state is an amalgamation of a few different companies, a few different ideas, a few different industries, which is really cool from a development and a cross-pollination aspect. We both do research and development and also manufacture instrumentation in Colorado, in Fort Collins, Colorado. And the named part of our business, Handix Scientific, was founded in 2015 by Dr. Ping Chen. And Handix from the beginning has focused on atmospheric science and from that end of aerosol science, so the atmosphere. And then the other part of our business, which was acquired and we were merged together into one company in 2022, two small businesses, both in the Fort Collins area, is Aerosol Devices, which was a joint company formed between Pat Keedy, a long-time person in the aerosol industry, and then Suzanne Herring, notable for not just this company, but Aerosol Dynamics as well, and the variety of scientific developments and work that she has done as well. And so the combining of those two companies brought new scientists, new ideas, and merging of these multiple products and genres of the aerosol field. So now all of us are developing aerosol instrumentation with the help of SBIR grants, with collaborations from groups like University of Miami, and also from personal investments and commercial endeavors as well. We also have gotten a variety of scientific grants and worked with agencies such as the NIH, the DLA, NASA, and groups like that. So we just wanted to acknowledge them with logos at the bottom of the slide here. Cool. So as an overview, before I go into everything, you'll see that we have a variety of products, once again, in kind of two general spheres. We have particle collectors on the left, which I'll go into more detail on each and how they go in theory at our demonstration coming up. We have the BioSpot Gem, our smallest aerosol collector, which is aimed more at bioaerosol collection, as well as our largest collector, the BioSpot Vivis, which is also aimed at bioaerosol collection, but with a much higher flow. Vivis to some people, Viva, interchangeable as you see fit, as well as our oldest product line, especially in the aerosol collection category, the spot sampler, which is notable for its time resolution capabilities and being used in more than just bioaerosol capture, being used in aerosol chemistry and atmospheric science, nanoparticle collection in other fields. We also have the Nano Spotlight, which is effectively a spot sampler technology paired with a nebulizer for use in ultra pure water and process fluid contamination issues for tiny nanoparticle contamination in ultra high purity process fluids. We also have the CFDC, which is a ice nucleation tool from the Handix atmospheric side of things, as well as additional products. And instead of talking about the POPs here, I will talk about the POPs on this slide. The Portable Optical Particle Spectrometer, or POPs, has been a technology at the Handix Scientific side of the business for quite some time. It's aimed to be a particle counter and sizer that has the ability to count and size particles from 130 nanometers to 3,000 nanometers, notable for being small and still research grade, but more affordable research grades, more expensive than cheap OPCs, but still provides a lot of scientific power for its small weight and size. Has been used in, I mean, there have been hundreds of these things sold, but used in a variety of airborne campaigns. You can see drones, balloon sondes. One of the things I like to highlight is that the POPs on a balloon has been flown into and burnt up in a volcano before, which I think is so rad. Generally speaking, a long time used and trusted tool for particle counting and sizing in this atmospheric measurement field. The other kind of primary technology that Handix/Aerosol Devices utilizes, sells, collaborates on, and manufactures are water condensation growth tube collectors. And I kind of like to start with why this specific technology would be useful or important, because collecting aerosol you can do with a filter, and our instruments, if you think about it, abstractly enough, are a glorified air filter. The three things that I think make these instruments unique is high efficiency capture of particles across a wide size range from 5 nanometers to 10 microns, viable capture of virus, bacteria, or other microbes, or if you're looking for genomic preservation, DNA RNA, not necessarily viability, you're gently capturing bioaerosols, which is nice. And then having a really concentrated and yet convenient sample ready for analysis onto surfaces like SEM stubs or Petri dishes or liquid vials that may be less accessible for a traditional filter sample that you might need to extract from. Just to save on time, I'll give this as a nice little teaser for when we actually talk about the technology a bit better. But long story short, think about utilizing water in the same way the human lung does to collect small particles and up in a gentle fashion with high efficiency. One of the things that I wanted to highlight specifically today, I don't think we've ever had a more dense collection of people that have utilized and developed, grown, improved the reach of this technology in this room. So thank you to everybody here, University of Miami, University of Florida, Westall, everybody and beyond. This specifically, there's a whole lot of people here that have made the Vivis, the GEM, and the Spot Sampler more than what it once was. Because if you look at any of the the papers on this technology, you'll see names of people in this room, which is super cool. But our technology has interesting comparisons to other specifically bioaerosol sampling technology for having much higher efficiency at lower particle sizes, which is useful. But also generally, if you compare to technologies like the SKC biosampler, higher viable or infectious capture of viruses and bacteria, which can be really useful for research and beyond. Sweet, I'll power through this because I'm getting close to the end. A wide variety of applications of our sampling technology specifically include things like viable or infectious bioaerosol capture in for example, this New York Times article that highlighted University of Florida's study capturing SARS-CoV-2, which is really cool, but also cloud ice nucleation characterization, the SYNC system that we use to detect Pseudomonas syringae in the air, as well as even on cruise ships. The possibilities of sampling aerosol of any type are as wide as the research applications of aerosol science could be, as long as you want to physically collect it. And with that, a few seconds over, thank you very much for your time, and I'll move on to the next person.
Okay, so our next speaker is going to be Josh from Sunset Laboratory.
All right. Thanks, everyone. I'm Josh Dixon from Sunset Laboratory. We manufacture and sell carbonaceous aerosol analysis instruments. Oops, how do we advance?
Yeah, I need to activate it first.
There we go. So what I'm showing here is just probably our 3 flagship instruments that we manufacture. We have an offline, an online, and then a complementary autoloader that it goes with our offline instrument. We analyze particulate carbonaceous aerosol through a thermal optical method. We also are able to do some optical absorption measurements with our online instrument as well. We've brought the Model 4 online instrument that you see that I guess would be on your right. That's what's upstairs running. We'll go into detail a little bit more during the tutorial about how these instruments work. But just for background, the type of people that use our equipment, industrial hygiene is where we got our start. About 30 years ago out of Oregon, working with the U.S. government agency NIOSH. But from there, we've worked with numerous aerosol and atmospheric researchers, regulatory agencies, climate change, greenhouse gas researchers have all used our instrument, people interested in carbon, engine emission laboratories, and mine operators. You can actually, that's me on up there running our equipment underground. Our first instrument, which is kind of our original instrument, is the Model 5. This is the offline instrument where the user would collect their samples on a quartz-based filter. You introduce it in the instrument and you receive your results, like the printout you would see down here. It's available with FID and NDIR detectors, and it's fully automated. You can add to that instrument a what we call an autoloader, where you can preload up to 36 samples. It'll run unattended while you do other things in the lab. And then finally, we have this online instrument, which is what we have upstairs running. This instrument was developed after the offline instrument was developed, but we're able to measure organic carbon, elemental carbon, black carbon, and total carbon in an automated format in various types of situations. This instrument is fairly unique, where it does the organic, elemental carbon, and total carbon that people call OCEC. But in addition to that, it'll measure black carbon in real time as well. I think I'm going to keep it short and sweet and let the next person go.
So our final speaker will be Sotirios from Particles Plus.
Hi, everyone. Thank you so much for being here today. My name is Sotirios Papathanasiou, and I work for Particles Plus. I will just do a quick overview for all of our products. We have quite many, so I will be very fast.
Sorry. So this is
Is
it
it
okay?
full
That's
screen?
for the PDF. Then you
Okay.
Yeah, proceed like this.
Got it. Thank you.
Yeah.
So Particles Plus originally founded in 2011. The founder and co-founder of the company come from an extended experience in the industry of particle counters since 1990. Actually, they have worked at Lighthouse, RT, Met1, Adams, TSI, and eventually they built up Particles Plus with the help also of Air Technology. We are the only company that offers lifetime warranty for all of the products, as long as the products are calibrated inside the period that it is determined. And we have calibration systems and authorized resellers all around the world. Those are the calibrated authorized service centers, as you can see. And all of our products are very easy to use. They use an interface based on icons, so people can use the products easily. So as you can see here, we have many series, handheld devices for indoor air quality monitor, and also some particle counters, the 7 and 5000 series. It comes in many flavors depending on the specification everyone has. And we also have monitors for clean room applications, but also for ambient monitoring and OEM solutions as well. All of the products use the same technology inside. We design and manufacture the particle counters from the ground up here in the US, in Massachusetts, and we're able to measure with the OPCs particulates from 0.3 up to 25 microns, and we can go from 0.5 up to 75 microns. And we also provide different sizes, 6, 3, or up to 30 channels, depending the configuration. We provide also different ways for people to access the data. Everything is stored internally, but we also can export the information via Wi-Fi or Ethernet or USB to any media. Those are some of the variations. I would like to talk a little bit more about the ambient air quality series, the 10,000, 11,000, 12,000, 13, and 40,000, which combine or not, some of them, they are dual instruments and they have condensation particle counters inside or and optical particle counters. We can measure from 5 nanometer up to 25 microns. And with the CPC, which is a water-based CPC, we can also see the total number of particulates for the size of particles that we want to measure, nanoparticles. We also can express the values apart from number into PM, if this is important for some of the folks out there. This is the CPC, which we're going to talk more upstairs. As I mentioned, it measures from 5 nanometers up to 3 microns. It's a water-based CPC, and we use the near adiabatic expansion principle in order to coat the particles with water and make them bigger in order for the simple laser scattering technology principle to measure the particles. That allows us to drop down the price of the product and be able to have also a smaller package, which can be deployed on a balloon or aircrafts, vehicles, or whatever it is necessary. And other OPCs, as I mentioned earlier, we specialize on CPCs and OPCs, and we have a great variation of different products for those that they want to develop their own solution based on our turnkey solutions. And we also provide free software with all of our instruments in order for researchers or other people to be able to use and get the data out of the devices. For one device or multiple devices, create plots, 2-axis plots, fully customizable, very easy to use. And some other products that they are coming soon are portable products. And thank you.
Okay, so now I think we can start our hands-on session on the 3rd floor. So before we go, I also want to remind everyone that after the hands-on session, let's come back to the 1st floor for a group picture. And then after that, we will have divide the attendees to 2 groups. One group will take a look at the blimp system here, and the other group will go to the MacArthur Engineering Building to look at our engineering laboratories. And then after a 20-minute tour, and then we'll switch these 2 groups. So rotate and then get another experience. Okay, so then after the tours, we'll conclude our session today. All right, so now let's go to the 3rd floor.
Number one, publications, and I recall the banks that are quite almost a decade worth of publications. So, you know, we decided we need for this thing where there's some places that's still a legitimate publication. So we're retaining these and beyond.
No, nice to meet you. Heard a lot.
And then we get.
Sounds like a need. Yes, good.
We even talked about it when we were reviewing the slide.
Good. Wonderful.
I know. I was listening to it too.
Yeah, I've never found something out. Or getting an email because half of the customers. Yeah, so the brand penetration of. So it's like, which by all do, even if you get what's made up logo on them, it's just now green instead of. Yeah, they look pretty sick. Actually, I just have. I should have, they're the Joe stickers that go on the. They probably go. Is this gonna be vacant or just like stuff?
Yeah, I don't know.
Oh, cool. Thank you so much. I appreciate it. Awesome. You know everything that's going on. It makes me feel so much more comfortable.
No, I need to watch the stuff belongings from.
Okay.
So send it. See what you're talking about. The newspapers organize all the newspapers edited to. Oh. So in the added to the table, I see this table, I need to change the. Let me share my screen. I'll share my screen and then you can.
아니 그러면 이거를 제가 일단은 갔을 때 지금 파일을 이메일을 내가 뜨려고 하는 파일을 수업을.
So I know there's the.
제가 손댔어. 번째는 여기 있는 거에서 있는 거.
This is awesome. And have you added that information into the.
그거는 저기 이게 왜냐면 어디서 제가
And send me those that you say you can access, so I can.
제 영역이 아니에요. 어디
Okay, so I'm gonna have to go through all of those that you know as well.
Nice.
Yes, I will do that. I think I'm gonna do it. This is awesome. The questions are coming in.
저 제가 할 수 있는 부분은
So that really. To see.
제가 좀
Take some samples of. So you don't have to give me an answer now. going to have some time to reflect. Let's finalize this. I'm gonna try to go over. And try to see. That mention even though we need to do some. You want to create a new city, and I will start looking at it. The same thing can be used, so we can find this community. But also we can see what we need. This will be to figure out how we need to.
그러면은 위기적 그분이 저희 좀 제가 안 그래도 인사 취재를 아예 안 계셨어요. 집에서 일하셨죠. 그런데 제가 안 그래도 하고 이게 자꾸 같은 일을 저도 같은 리스폰스만 할 수가 없어요. 아니 그러니까 자꾸 차갑게 보시는데 뭐를 요청하는 진짜 아니었는데 거기에 없으면 없고 그러면은 이 정도 이거는 그냥 펜션을
Okay, so I'll refer you. Thank you for the review. Wow. Yeah,
Hi. Hi, Zoom attendees. I think today's session, the rest will be hands-on experiments and instruments demos. So feel free to log off because I don't think we will present here. Thank you.